Good evening. Wherever you are right now, whatever the quality of the light in your room, just settle in for a moment. Feel the weight of the air, the texture of the surface beneath your hands. There is no need to rush. Curiosity can take its time tonight. We are not here to argue a case or to win a debate. We are here to sit with a question, to let it unfold slowly like a map of a place no one has ever visited, but whose existence we can infer from the faintest of signals. The work of this moment is simply to be present with a sense of wonder, to hold a mystery without the immediate need to solve it. It's a practice in slowness, in allowing complexity to reveal itself without force. Think of the ground beneath you. Beneath the floor, beneath the foundation of the building you're in, beneath the soil and the pavement, there are layers of rock. And those layers are a kind of archive, a library of immense and almost incomprehensible age. Each stratum holds the memory of a different world, a different sky, a different ocean. We live atop this deep history, mostly unaware of the profound transformations that are recorded, silently, just a few miles below our feet. The story of our planet is not just a story of change, but of worlds layered upon worlds. And so, we are going to travel down through those layers tonight, not with a drill, but with our imagination, guided by the careful work of science. We will bypass the age of dinosaurs, slip past the first forests that greened the continents, and move deeper still into a time so remote that the very texture of reality feels alien. A time before animals, before plants, before fungi. A time when the hum of the planet would have been a different frequency altogether. We are going to try and inhabit a single moment from this deep past. And as we settle into this shared space of inquiry, letting the noise of the day fall away, I want to offer just one elegant question to frame our journey. It's a question that invites speculation, but is anchored in evidence, a question that touches upon the very nature of time, life, and planetary being. It is this: what does it mean for a world to be quiet, and what kind of power is held in that quietness? This question will be our compass. It steers us away from a simple catalogue of facts and figures and toward a more felt understanding of a world that existed 2 billion years ago. It asks us to consider not just what was happening, but the quality of how it was happening. Was it a world in stasis, or was it a world engaged in a slow, planetary-scale process of becoming? Was its quietness an absence of activity, or was it the sound of a foundation being laid, stone by monumental stone in the dark? We will explore this together, without assumption, and with a shared sense of patience. The answers, if they come at all, will not be simple declarations, but rather a series of unfolding perspectives, each adding a new layer of texture to our understanding. For now, all that is required is your attention and a willingness to travel to a very, very old place. Let's begin there. Before we journey into the specifics of this ancient Earth, it's important to establish the lens we'll be using and the guardrails that will keep our exploration grounded and honest. This is our method, our shared agreement for how we will approach the immense mystery ahead. The goal tonight is not to arrive at a final, unshakable truth. The deep past is far too fragmented, and the evidence far too sparse for that kind of certainty. Instead, our purpose is to build a plausible model, a working hypothesis that we can step inside, look around, and inhabit for a little while. Think of it less like a photograph and more like a carefully rendered sketch, based on every clue we can find. The first principle of our inquiry is that we will favour questions over answers. Certainty can often close down curiosity, while a well-posed question opens up new avenues of thought. We are detectives examining a scene where most of the evidence has been weathered away, erased by 2 billion years of geology, chemistry, and biology. What remains are traces. The chemical signature in a sliver of rock, the faint pattern in a sedimentary layer, the isotopic ratio in a microscopic crystal. Our work is to interpret these fragments, to ask what kind of world could have produced them. This process is inherently provisional. Any model we build must be held lightly, ready to be revised, or even discarded when a new piece of evidence emerges. So, as we proceed, you will hear me use cautious language, words like might, could, suggests, and tends to. This isn't a sign of weakness in the science. It is a sign of its strength. It is the signature of intellectual honesty, an acknowledgement of the boundaries of our knowledge. The second guardrail is our commitment to avoiding absolutism. The history of science is filled with grand, overarching theories that were later found to be too simple. The real world, and especially the living world, is rarely a matter of either-or. It is almost always a matter of both and, of continua, of shifting balances. We will resist the temptation to paint a picture in sharp blacks and whites. Instead, we will look for the shades of grey, the dynamic equilibriums, the feedback loops that can create long periods of stability that only look like stasis from a distance. The world we are visiting was not a static diorama. It was a living system with its own rhythms and behaviours, most of which operated on timescales far beyond our intuitive grasp. Our method, then, is one of synthesis. We will gather threads from different scientific disciplines, geology, atmospheric chemistry, biology, planetary science, and attempt to weave them together into a coherent tapestry. But we will also pay attention to the seams and the gaps. Where does one model not quite fit with another? What are the known unknowns? By highlighting these areas of uncertainty, we aren't undermining the project. We are making it more robust. We are mapping the edges of the territory we are exploring. This is crucial because our goal is not to present a seamless, perfect story. A perfect story about a 2-billion-year-old world would be a work of fiction. A real, scientific exploration is messy, incomplete, and always evolving. Finally, we will make a conscious effort to separate observation from interpretation. First, we will look at the evidence itself, the composition of a rock, the structure of a fossilized microbial mat, the calculated distance of the moon at that time. We will describe what is there. Only then will we move to the next level, asking, what might this imply? What kind of processes could lead to this result? This two-step process, describe, then infer, helps keep us tethered to the ground truth, preventing our imaginations from running too far ahead of the data. It is a discipline of slowness, of methodical construction. We are building our model brick by brick, checking the foundation at every step. So, to be clear, our journey tonight is not a lecture delivering settled facts. It is an invitation to participate in the process of scientific inquiry itself. It is an exercise in building a provisional understanding of a world that is almost impossibly distant, yet is foundational to the world we inhabit today. We are embracing inquiry over certainty, provisional models over final answers, and the slow, careful work of weaving together disparate clues into a story that is as honest and as wondrous as we can make it. Let's bring this out of the abstract and into the immediate. Right now, in this moment, take a second to simply arrive where you are. Feel the chair or the floor supporting you. Notice the specific temperature of the air on your skin. Is there a draft from a window or the gentle hum of a heating or cooling system? The world is speaking to you in these quiet, sensory details. Our journey into deep time doesn't begin by leaving our bodies behind. It begins by grounding ourselves within them, right here, right now. Your body is the vessel for this exploration, the only instrument you truly have for perceiving and making sense of the world. Let's do a quick inventory of this present moment. There is the air you are breathing. Take a conscious breath. Feel the sensation of your lungs expanding and contracting. That air is composed of roughly 78% nitrogen, 21% oxygen, and a handful of other trace gases. That specific mixture, especially that high concentration of free oxygen, is the defining feature of our modern atmosphere. It is what fuels the fire of your metabolism, what allows for the kind of active, energetic life we know. Remember the feeling of this breath. We will be returning to it as a point of contrast. Now, consider the light in the room, whether it's the warm glow of a lamp or the cool, fading light of dusk outside a window. It has a certain quality, a certain colour. This light is filtering through our specific atmosphere. The sky is blue on a clear day for a reason, because of the way particles in our air scatter blue light more effectively than red light. The colour of the sky is a direct consequence of the air's chemistry. Keep that in mind too. The colour of the light is a clue about the world it is passing through. And what about water? Perhaps you have a glass of water nearby. It's clear. If you were to look at a deep body of water, like a lake or an ocean, it would appear blue, again due to the way it absorbs and scatters light. This clarity, this blueness, is a feature of our world's chemistry. It tells us that our oceans are oxygenated, that the elements dissolved within them are in a particular chemical state. These are our baselines: a high oxygen atmosphere, a blue sky, clear blue oceans, a day that lasts for 24 hours, giving a certain rhythm to our lives, our sleep, our biology. The steady pull of the moon, creating a predictable and relatively gentle tide. These sensory inputs are so constant, so fundamental to our experience of being alive, that we rarely even notice them. They are the invisible architecture of our reality, the stage on which all of human history has played out. But every single one of these details, the air, the light, the water, the length of a day, is a planetary contingency. It is not a given. It is a feature of this specific era in Earth's long history. And to understand the world of 2 billion years ago, we have to be willing to change every single one of them. We have to strip away the familiar sensory landscape of our present and build, from the ground up, a world with a different set of rules, a world with different air, a different coloured sky, and a profoundly different rhythm. This act of grounding ourselves in the here and now is not just a preamble, it is a crucial part of our method. By becoming acutely aware of the physical reality of this moment, we create a stable reference point. It is from this specific, sensory-rich location in space and time that we can begin our journey outward and backward. We are tethered to the present, which allows us to explore the deep past without losing our bearings. So take one more breath of this familiar, oxygen-rich air. Feel the familiar 24-hour rhythm in your bones. Look at the familiar quality of the light. This is our home. This is Earth now. And from here, we will begin to imagine Earth then. It is fair to ask why we should even bother with this exercise. Why dedicate this time and attention to a world so ancient that it seems to have no direct bearing on our lives? 2 billion years is a number so large that it defies human intuition. It is 1,000 times older than the earliest modern humans, 10,000 times older than the dawn of civilization. Why does this quiet, distant world matter? The answer, I think, lies in understanding the difference between an event and a foundation. Our lives are governed by events, by things that happen on timescales of days or years or generations. But all of these events unfold upon a foundation that was built on timescales of eons. Exploring that foundation is an act of understanding the fundamental operating system of our planet. On the human scale, the stakes are about perspective. We tend to view the state of our current world as normal, as the default. The climate we enjoy, the composition of the atmosphere, the stability of the continents, it all feels permanent. But the journey to 2 billion years ago reveals that every one of these things is a temporary arrangement. Our planet is not a static object. It is a dynamic system that has passed through radically different states. The Earth of the Proterozoic eon was, in many ways, a different planet. It had a different metabolism. Understanding this gives us a profound sense of humility. It replaces our unexamined assumption of stability with a deeper appreciation for the long, slow, and often precarious processes that created the world we depend on. It reframes our present moment not as the end point of history, but as a thin, fragile layer resting atop an immense and ever-shifting deep time. Zooming out to a geological timescale, the stakes become even clearer. The period we are visiting, roughly 2 billion years ago, falls within an era that some geologists have called the Boring Billion. The nickname comes from the perception that for about 1 billion years, from roughly 1.8 to 0.8 billion years ago, not much happened. The climate was stable, atmospheric oxygen levels were low and constant, and the pace of evolution seemed to slow to a crawl. But this perspective is changing. Many scientists now see this period not as boring, but as crucial. It may have been the time when the Earth's systems, its tectonic engine, its climate regulation, its biogeochemical cycles were being fine-tuned. It was a period of planetary stabilization. Think of it like building a complex piece of machinery. There's the exciting phase of initial invention and assembly, and then there's the long, patient phase of testing, debugging, and calibration. The Boring Billion might have been Earth's long calibration phase. It was during this quiet era that the feedback loops connecting life and the planet were established and strengthened. The world was learning how to regulate itself. This is not a boring story. It is the story of how our planet developed the resilience that has allowed it to maintain liquid water and habitable conditions for billions of years, despite a brightening sun and countless cosmic and terrestrial shocks. The quietness of that world was not an absence of activity. It was the hum of a system achieving a new and profoundly important kind of equilibrium. The implications for our understanding of life in the universe are also significant. When we search for life on other planets, what are we looking for? We often look for worlds that look like modern Earth. But what if a planet can be alive and have a thriving biosphere, but look completely different? What if it looks like Earth 2 billion years ago? A world with a methane haze in its atmosphere, with oceans rich in dissolved iron, with life that is entirely microbial. This deep time perspective widens our definition of what a living planet can be. It teaches us that habitability is not a single state, but a long evolutionary journey. A planet might spend 1 billion or 2 billion years in a boring microbial phase before the conditions are right for the explosion of complex macroscopic life. So, why does it matter? It matters because the quiet world of 2 billion years ago is the hidden architecture of our own world. It holds the story of how our planet's life support systems were built. It provides a humbling context for our own fleeting moment in the sun, and it expands our imagination about what it means for a planet, anywhere in the cosmos, to be truly alive. The stakes are not about immediate survival, but about a deeper kind of wisdom, the wisdom of timescales, of systems, and of the long, slow foundational work that makes everything else possible. As we begin to sketch the outlines of this ancient world, a few key threads immediately emerge from the scientific data. These are lines of inquiry, sub-questions that will guide our exploration. We won't resolve them right away. Instead, let's just put them on the table, like clues at the start of a mystery. We can think of them as open loops that we will promise to return to and weave together as our picture becomes clearer. The first thread concerns the air itself. We know that the great oxygenation of Earth's atmosphere had already begun by this point, thanks to the revolutionary invention of photosynthesis by cyanobacteria. But the process was not a simple, linear rise. For a very long time, oxygen levels remained low and stable, perhaps only a few % of what they are today. This raises a fascinating question. What was holding the system in that state? Why didn't oxygen levels continue to rise rapidly? This suggests the presence of powerful regulatory systems, planetary-scale feedbacks that were balancing the production of oxygen with its consumption. Understanding this great pause in oxygenation is key to understanding the planet's metabolism at the time. We will need to investigate the great sinks that were absorbing this reactive gas, and what that meant for the chemistry of the entire world. The second thread has to do with the pace of life's evolution. 2 billion years ago, the most complex life forms on the planet were likely the first eukaryotes, cells that had a nucleus and other internal structures, the ancestors of all animals, plants, and fungi. This was a monumental leap in complexity from the simpler prokaryotic cells, like bacteria, that had dominated the planet for over 1 billion years. Yet, after this initial innovation, macroscopic multicellular life still seems to have been a very long way off. Why? What were the environmental or genetic barriers that kept life microscopic for so long? Was it the low oxygen levels, a lack of key nutrients, or was there an intrinsic difficulty in making the leap to true multicellularity? This question pushes us to think about the relationship between a planet and the life that inhabits it. Does the planet dictate the pace of evolution, or does evolution proceed according to its own internal clock? We will return to this tension between environmental constraint and biological innovation. And the third thread is about the physical stage itself, the arrangement of the continents and the rhythm of the planet's days. 2 billion years ago, Earth's land masses were likely gathered together into one of the planet's first true continents. Supercontinents, a vast contiguous land called Columbia, or Nuna. At the same time, the Moon was significantly closer to the Earth, making the planet spin faster. A day was not 24 hours long, but perhaps closer to 19 or 20. This creates a cascade of physical consequences: more powerful tides sweeping across shallow seas, a different pattern of atmospheric and oceanic circulation, and a vast continental interior with a climate unlike anything on Earth today. How did these physical realities shape the biosphere? How did a shorter day and a giant continent influence the feedback loops of oxygen, carbon, and life? We will need to connect the geological story with the biological one. These three threads, the puzzle of the atmosphere, the pace of evolution, and the planet's physical rhythm, are our starting points. They are not separate inquiries. As we will see, they are deeply interconnected. The amount of oxygen in the air is tied to the evolution of life, which is in turn influenced by the geography of the planet and the length of its day. Our task will be to follow each thread, to see how they cross and knot together, and to build a model where these different elements can coexist and interact in a plausible way. For now, just hold them in your mind as markers for the journey ahead. We will pick them up again shortly. To build a shared understanding, we need a shared language. The vocabulary of deep time can be dense with jargon, so let's pause here to define a few key terms and lay out the core assumptions we'll be using. Our goal is plain language, to translate these specialized concepts into more intuitive ideas. First, let's talk about time itself. When we say 2 billion years ago, we are placing ourselves in the middle of the Proterozoic eon. An eon is the largest division of geologic time. Earth's history is divided into four of them: the Hadean, the fiery beginning; the Archean, the time of early life and low oxygen; the Proterozoic, our focus; and the Phanerozoic, the last 540 million years, which includes the dinosaurs and us. The Proterozoic eon stretches from 2.5 billion to about 540 million years ago. It's a vast stretch of time, and our target, 2 billion years ago, sits within a period often nicknamed the boring billion, as we've mentioned. We'll be challenging that nickname, but it's a useful label for now. The key assumption here is that we can measure this time with a high degree of confidence using radiometric dating of rocks, particularly of tiny durable crystals called zircons, which act like geological clocks. Next, let's define the stage, the planet's geography. We will be talking about a supercontinent. A supercontinent is simply a landmass made up of most or all of the Earth's continental crust. We are familiar with the most recent one, Pangea, but geologists have found evidence for several earlier ones. The one that likely existed around our target time is called Columbia, or sometimes Nuna. Our working assumption is that the fundamental engine of plate tectonics, the slow movement of continental and oceanic plates, was already operating, much as it does today, albeit perhaps with some differences in style due to a hotter mantle. This tectonic engine is what brings continents together and pulls them apart, a slow dance that fundamentally shapes climate and evolution over millions of years. Now for the actors, the life of this era. The dominant life forms were microbes. Specifically, we'll talk about two main types. First are the prokaryotes, which are simple, single-celled organisms without a nucleus, like bacteria and archaea. They had already been running the planet for over 1 billion years. Within this group, a key player is cyanobacteria, the microbes that invented oxygen-producing photosynthesis. You can think of them as the microscopic engines that began to terraform the planet. The second group, which was just emerging, are the eukaryotes. These are the cells that make up all complex life today, including us. A eukaryotic cell is fundamentally different. It's larger, more complex, and contains specialized internal compartments, including a nucleus to house its DNA, and, crucially, mitochondria to generate energy. Our assumption is that eukaryotes arose through a process called endosymbiosis, where one simple cell engulfed another and they formed a cooperative symbiotic relationship. This leads us to the environment they inhabited. We will refer to the atmosphere as disoxic or suboxic. This just means it had very low levels of free oxygen, perhaps 1 to 10% of present-day levels. The oceans were likely anoxic, lacking oxygen, in their depths, but with oxygenated surface waters, at least in some areas. A key feature of these oceans was that they were rich in dissolved iron. Today, Any iron that washes into the sea immediately rusts and falls to the seafloor because of the high oxygen content. But in a low-oxygen world, iron could remain dissolved, turning the oceans a pale green colour. When pulses of oxygen from cyanobacteria reach this iron-rich water, it would cause the iron to precipitate out, forming vast layers of iron oxide, rust, on the ocean floor. These layers are now preserved as banded iron formations, one of our most important clues about this ancient world. Finally, we need to think in terms of systems and feedback loops. A system is just a set of interacting parts that form a complex whole, in our case, the entire planet. A feedback loop is a process where the output of an action influences the continuation of that same action. A negative feedback loop is stabilizing. Think of a thermostat. When the room gets too hot, the thermostat turns the furnace off, which cools the room down. This tends to keep the system in a stable state. A positive feedback loop is amplifying. Think of a microphone held too close to a speaker. The sound gets amplified, which is then picked up and amplified again, leading to a loud squeal. Our core assumption is that the Earth operates as a complex system full of both types of loops, and that the long period of stability during the Proterozoic was the result of powerful negative feedback loops dominating the planet's behavior. So, to recap, we are in the Proterozoic eon, on a planet with a supercontinent governed by plate tectonics. The world is run by microbes, with eukaryotes just beginning to emerge. The atmosphere is low in oxygen, and the oceans are rich in dissolved iron. And all of this is interconnected through a web of systemic feedbacks. These are our working definitions and our foundational assumptions. With this shared toolkit, we can now begin to assemble a more detailed picture of this ancient Earth. To truly appreciate the world of 2 billion years ago, we need a brief sense of what came before. We don't need a detailed timeline, just a snapshot of the major planetary shifts that set the stage for our moment in the Proterozoic. This is the background context, the story so far in Earth's epic history. Our planet formed around 4.5 billion years ago, a hot, chaotic and sterile ball of rock. For the first few 100 million years, during the Hadean eon, it was a truly alien world, bombarded by asteroids and likely featuring a thick, suffocating atmosphere of carbon dioxide, water vapor and nitrogen, with no free oxygen at all. The surface was a magma ocean, slowly cooling and solidifying into the first crust. Sometime during this early violent period, a Mars-sized object is thought to have collided with the proto-Earth, and the debris from this cataclysmic impact eventually coalesced to form our Moon. This event was not just a dramatic sideshow, it was foundational. It set the initial tilt of Earth's axis, which gives us our seasons, and it established the Earth-Moon system, which has governed our planet's rotation and tides ever since. Life enters the story sometime in the next eon, the Archean, which began around 4 billion years ago. The evidence is faint and hotly debated, but by 3.5 billion years ago, we have solid fossil evidence of microbial life. These were the prokaryotes, the simple, single-celled organisms. For over 1 billion years, they were the sole inhabitants of a world that would have been utterly hostile to us. The sun was fainter then, perhaps only 75% as bright as it is today. To keep the planet from freezing over, the atmosphere must have contained a potent cocktail of greenhouse gases, likely including not just carbon dioxide but also significant amounts of methane, produced by some of those early microbes. The sky under this methane-rich atmosphere may not have been blue, but a hazy orange. The oceans were anoxic, without oxygen, and filled with dissolved iron. The great turning point, the event that truly began to shape the world we know, was the evolution of a new metabolic trick by a group of bacteria called cyanobacteria. Around 2.4 billion years ago, they figured out how to use sunlight, water, and carbon dioxide to create energy. This process, photosynthesis, had a revolutionary and highly toxic waste product, free oxygen. For the first time, large quantities of this highly reactive gas were being pumped into the environment. This triggered what is known as the Great Oxidation Event, or the GOE. It was perhaps the most significant pollution event in Earth's history. This new oxygen didn't immediately flood the atmosphere. For millions of years, It was consumed by reacting with things in the environment. It reacted with dissolved iron in the oceans, causing it to rust and settle on the seafloor, creating the vast banded iron formations that are our primary record of this event. It reacted with minerals on land and gases in the atmosphere. The planet essentially rusted on a global scale. This period was a battle between the old anoxic world and the new oxygen-producing biosphere. Eventually, these oxygen sinks became saturated, and free oxygen began to accumulate in the atmosphere for the first time. This brings us to the doorstep of our era, the Proterozoic eon, which begins at 2.5 billion years ago. The Great Oxidation Event was a planetary revolution. It wiped out vast ecosystems of anaerobic life, life that is poisoned by oxygen, and paved the way for new oxygen-breathing metabolisms. It fundamentally and permanently altered the chemistry of the planet's surface. So, when we arrive at our moment, 2 billion years ago, we are not looking at the beginning of the story. We are looking at the aftermath of this first great revolution. The world has already made the switch. Oxygen is now a permanent feature of the planetary system. But the revolution is not yet complete. The atmosphere is not like ours. The levels of oxygen are low, and they seem to have stalled. The planet has settled into a new kind of equilibrium, a state that would persist for another billion years. The question for us then is not, how did oxygen get here? But rather, now that it's here, what kind of world did it create, and why did that world remain so stable for so long? The dramatic upheaval of the GOE is over. The long, quiet, and deeply consequential age of calibration has begun. Let's begin our deep dive into the evidence by starting at a scale we can almost imagine, the human scale. If you could stand on the shore of an ancient sea 2 billion years ago, what would you see, feel, and breathe? Reconstructing this sensory experience is a powerful way to understand the fundamental chemistry of this lost world. We can't travel back in time, but we can use the geological record to piece together the patterns of this environment. The first thing you might notice is the air. Let's go back to that breath we took earlier. The air of the Proterozoic would have felt thin, not in pressure, but in its life-giving quality. With oxygen levels at perhaps only 5% of today's, a deep breath would not have been restorative. Vigorous activity would have been impossible for an oxygen-dependent creature like a human. The atmosphere was still mostly nitrogen, as it is today, but its trace components were profoundly different. The protective ozone layer, which is made of 3 oxygen atoms, O3, would have been much weaker. This means the unfiltered ultraviolet radiation from the sun would have been dangerously intense. Life on exposed land surfaces would have been extremely difficult, which is one reason why the biosphere was concentrated in the oceans and in microbial mats that could provide some measure of protection. Now, lift your eyes to the sky. What colour is it? We are conditioned to expect a vibrant blue, a result of sunlight scattering off nitrogen and oxygen molecules, a phenomenon called Rayleigh scattering. But in a world with low oxygen, another gas might have played a more significant role in the atmosphere's appearance: methane. Although the Great Oxidation Event had likely reduced the dominance of methane-producing microbes, methane was probably still a more significant component of the atmosphere than it is today. Methane can react in the upper atmosphere under UV radiation to form a thin organic haze, composed of complex hydrocarbon particles. This is not speculation. We see this exact phenomenon on Saturn's moon, Titan. A similar, though perhaps much thinner haze on the Proterozoic Earth would have given the sky a different tint. Instead of a deep blue, the sky might have been a pale, washed-out orange, or perhaps a faint pinkish yellow. The colour would shift depending on the angle of the sun, but the crisp, brilliant blue we know would have been absent. Sunsets and sunrises, with sunlight passing through more of this haze, could have been spectacularly colourful. Now, turn your gaze to the ocean. Here, the difference would be just as striking. Our modern oceans are blue because water absorbs longer, redder wavelengths of light, and the scarcity of particles means the blue light is scattered back to our eyes. But the Proterozoic ocean was not empty. It was a chemical soup rich in dissolved ferrous iron, Fe2+. Water with high concentrations of dissolved iron has a distinct colour. It's not brown or rusty. That happens when the iron oxidizes. In its dissolved, reduced state, it would have imparted a pale green hue to the water. So, instead of a blue ocean, you would be looking out at a vast pale green sea stretching to the horizon. Imagine the scene, a pale orange sky meeting a pale green ocean. The colours are muted, alien. The very palette of the world is different. This isn't just an aesthetic detail, it's a direct visual manifestation of the planet's chemistry. The sky is orange because there isn't enough oxygen to scrub the methane haze. The ocean is green because there isn't enough oxygen to cause the dissolved iron to precipitate out. These two facts are two sides of the same coin. The world is in a chemically reduced state, a state of oxygen poverty, compared to our own. The mechanism here is the global balance between oxygen sources and sinks. Cyanobacteria in the surface waters were the source, steadily producing oxygen through photosynthesis. But the sinks, the things that consume oxygen, were enormous. The deep ocean, rich in dissolved iron and other reducing compounds, was a vast chemical buffer, swallowing up much of the oxygen that was produced. Any oxygen that mixed down from the surface would immediately react with the iron, which would then precipitate as iron oxides, falling like a slow, constant rain of rust to the seafloor. This process is what created the banded iron formations. It was a planetary scale titration. The biosphere was adding oxygen, and the geosphere was removing it. The low-level equilibrium we see, the orange sky, the green ocean, was the result of this grand balance. The implication of this is that the world was living on an oxygen budget that was orders of magnitude smaller than today's. This profoundly constrained the possibilities for life. The energy-intensive metabolisms that power large, active animals were simply not possible. The biosphere was trapped in a low-energy state. The world was quiet not just because there were no animals to make noise, but because the entire global system lacked the energetic fuel that high oxygen levels provide. This brings us to a question that hangs over this entire sensory reconstruction. We see a system in a stable, low-energy state. Was this state inevitable? Was it a permanent trap, or was it a necessary long-term phase of planetary development? And what could possibly have been powerful enough to eventually break this equilibrium and allow oxygen to finally accumulate to the levels we breathe today? Let's now test the boundaries of the model we've just built. We've established a world with a weak ozone layer, a hazy sky, and iron-rich green oceans, all stemming from a low-oxygen equilibrium. What are the edge cases for this model? Where is it most fragile? And what does it imply about the lived experience of the biosphere? First, let's stress test the idea of stability. We've described the system as being in a long, quiet equilibrium, but was it uniformly quiet? Probably not. The balance between oxygen sources, photosynthesis, and oxygen sinks, dissolved iron, volcanic gases, weathering of rocks, was likely dynamic. It's plausible that this stable state was punctuated by periods of fluctuation. For example, a massive volcanic eruption could release huge quantities of reducing gases, temporarily drawing down atmospheric oxygen. Conversely, a major tectonic event that created vast new shallow seas could have led to a boom in cyanobacteria populations, causing a temporary pulse of oxygen. These pulses are what geologists call oxygen oases or whiffs of oxygen. Imagine what this would mean. For thousands of years, the ocean might become slightly less green, the sky a little less hazy. During these periods, the newly emerging eukaryotes, which require oxygen, might have flourished and spread. Then, as the sinks reasserted their dominance, the system would slump back to its low oxygen baseline, and these nascent eukaryotic communities might have collapsed. This creates a picture not of perfect stasis, but of a kind of planetary breathing, with oxygen levels slowly oscillating around a low baseline. This would have been a profound driver of evolution. It would have created intense selective pressure for organisms that could tolerate, and perhaps even thrive in, environments with fluctuating oxygen levels. The ability to survive these long-term environmental swings might have been one of the key adaptations that set the stage for later, more complex life. Now let's consider the boundaries in space, not just in time. The world was likely not homogeneous. The supercontinent Columbia would have created distinct environmental zones. The vast interior of this landmass would have been extremely arid, a sterile desert under a harsh UV-drenched sky. life would have been almost entirely absent there. The true engines of the biosphere were in the oceans, but even there, conditions would have varied dramatically. We can imagine coastal shelves and shallow inland seas as the vibrant heartlands of this world. Here, sunlight could penetrate the water, fueling massive communities of cyanobacteria, forming extensive reef-like structures called stromatolites. These regions would have been the oxygen oases, where local oxygen concentrations in the surface water might have been significantly higher than the global average. Step just a little farther out to sea, however, and you would cross a sharp chemical boundary, a chemocline. Below the sunlit, oxygenated surface layer, the deep ocean would have remained profoundly anoxic and iron-rich. This created a layered, or stratified, ocean. The boundary between these two layers would have been a zone of intense chemical activity, a place where the new oxygenated world met the old anaerobic one. What kind of life could exist at such an interface? Perhaps this is where the most innovative evolution was happening, driven by the steep chemical gradients. This model of a patchy, heterogeneous world has important implications. It means that when we look for evidence of early life, we shouldn't expect to find a uniform signal. The geological record in one location might tell a story of a relatively oxygen-rich environment, while rocks of the same age from another location might indicate a completely anoxic one. This isn't a contradiction, it's a reflection of the world's complexity. It also means that the emergence of new life forms, like the eukaryotes, might have happened in isolated pockets in these sheltered, resource-rich oases long before they were able to expand and dominate the global ecosystem. They were living on the edge, surviving in the margins. This stress testing of our initial model replaces a simple, static picture with a much more dynamic and interesting one. The quietness of the Proterozoic was not the quiet of a dead world, but the complex, negotiated quiet of a system with powerful stabilizing forces. It was a world of sharp chemical boundaries, of long-term oscillations, and of isolated pockets of innovation. It preserves the core idea of a low oxygen equilibrium, but it adds texture and nuance. It suggests that the true story of this era is found not in the average conditions, but in the exceptions, the boundaries, and the moments of instability that punctuated 1 billion years of calm. To understand the immense stability of the Proterozoic world, we need to zoom out from the human-scale sensory experience and look at the planet as an integrated system. The key to this perspective is the concept of feedback loops, the processes that can either stabilize or destabilize a system. The quietness of this era was not an accident. It was an emergent property of a planet that had developed powerful negative feedbacks, acting like a global thermostat. Let's trace the primary feedback loop that likely governed the planet at this time. The system involves the interplay between climate, geology, and biology. The starting point is photosynthesis by cyanobacteria in the shallow oceans. This process does two things. It produces oxygen, and it draws down carbon dioxide, CO2, from the atmosphere, turning it into organic carbon. This organic carbon then gets buried in sediments on the seafloor. Now, let's follow the consequences. Drawing down CO2, a potent greenhouse gas, has a cooling effect on the planet. If this process were to run unchecked, the planet would get colder and colder, eventually leading to a runaway ice age. But here, a geological feedback kicks in. As the planet cools, the rate of rock weathering on the continents slows down. Rock weathering is a key process that consumes CO2 from the atmosphere. So, cooling slows down weathering, which means less CO2 is consumed, which leaves more CO2 in the atmosphere, which in turn warms the planet back up. This is a classic negative feedback loop, a planetary thermostat. It works in the other direction too. If the planet gets too warm, weathering speeds up, drawing down more CO2 and cooling the planet. This cycle, known as the carbonate-silicate cycle, is thought to be the primary long-term climate regulator on Earth. But in the Proterozoic, this cycle had a crucial biological component. The burial of organic carbon from photosynthesis was also removing CO2 from the atmosphere. This biological pump was working in concert with the geological thermostat. Let's imagine what happens. If there's a boom in cyanobacteria, they draw down a lot of CO2, which starts to cool the planet. This cooling might then slow down the biological activity, reducing the rate of CO2 drawdown and allowing the climate to stabilize. It's a coupled system where life influences the climate, and the climate in turn influences life. Now let's add oxygen back into the mix. The production of oxygen is tied to the burial of organic carbon. If organic carbon is created and then immediately consumed by other microbes, a process called respiration, the oxygen is used up, and there is no net change. To get a net increase in atmospheric oxygen, you have to bury the organic carbon, sequestering it away from the oxygen it was created with. This means that the same process that was cooling the planet, the burial of organic carbon, was also the source of atmospheric oxygen. This reveals a beautifully interconnected system. Tectonic activity could create new shallow seas, leading to more biological productivity. This would lead to more organic carbon burial, which would cause a pulse of oxygen and a drop in CO2, cooling the climate. This cooler climate would then slow things down, creating a feedback that prevents runaway change. The entire system, tectonics, climate, and life, is coupled. The stability of the Proterozoic can be seen as a state where these coupled feedback loops achieved a remarkable balance. The sources of oxygen were balanced by the sinks. The drawdown of CO2 was balanced by volcanic outgassing and the slow weathering thermostat. It's crucial to understand that there is no intention or design in this system. The planet is not trying to be stable. Homeostasis, the tendency toward a stable equilibrium, is an emergent property. It arises spontaneously from the interactions of countless individual processes. The system settles into a state that is resilient to perturbations because of the nature of its internal feedback loops. This perspective is powerful because it explains both the long period of stability and why it was eventually broken. A system like this is stable within a certain range of conditions, but if a perturbation is large enough, for instance a dramatic change in tectonic activity or the evolution of a new kind of organism that radically alters the carbon cycle, it can push the system across a threshold into a new stable state. The Proterozoic world was a system that had found its groove. It had stumbled upon a set of interlocking feedbacks that kept it in a low-oxygen, temperate state for 1 billion years. It was a mature, self-regulating system. The quietness was the hum of this intricate global machinery, operating smoothly and efficiently in the background. Understanding this systems-level view is key to appreciating the profound and deeply unboring nature of this ancient world. The existence of these powerful, self-regulating feedback loops has consequences that ripple through the entire Earth system. These are the second-order effects, the if-then chains that emerge from the logic of a coupled world. If the planet is in a state of strong homeostatic regulation, then what does that imply for the evolution of life and the development of the world? First, if the system is highly stable, it implies a certain degree of environmental predictability over long timescales. While there might have been short-term fluctuations, the overall baseline, low oxygen, moderate temperatures, was reliable. This predictability has a profound effect on evolution. In a stable environment, there is less pressure for radical innovation. Evolution might tend toward optimizing for the existing conditions rather than exploring completely new ways of being. This could be one of the key explanations for the so-called boring billion. The stability of the environment itself may have throttled the pace of evolutionary change. Life had settled into a successful strategy for the existing world, and the planetary system was so well regulated that it didn't provide the kind of large-scale environmental shocks that often drive rapid evolutionary diversification. This leads to a second implication. The system was likely very resilient to small-scale disruptions. A local volcanic eruption or a minor change in solar output could be easily absorbed by the planet's powerful negative feedback loops. The planetary thermostat was robust. This is a crucial feature for long-term habitability. A planet that can maintain stability in the face of minor challenges is a planet where life can persist for billions of years. So, the boring nature of this period can be reframed as a sign of planetary health and maturity. The system was good at maintaining its equilibrium. It wasn't fragile, it was tough. However, this very robustness might have a hidden downside. A system that is highly optimized for one state can sometimes be vulnerable to collapse, if it is pushed too far outside its comfort zone. Think of a finely tuned engine. It runs perfectly under specific conditions, but if you introduce a different type of fuel, it might fail catastrophically. The Proterozoic Earth system was tuned for a low-oxygen microbial world. The emergence of a new biological innovation, for example, the evolution of the first simple animals that could graze on microbial mats, could represent a new kind of fuel. If such an innovation were to occur, it might initially be suppressed by the stable conditions, but if it managed to gain a foothold, it could begin to fundamentally alter the system's feedbacks. Grazing animals could reduce the coverage of microbial mats, which could change the rate of organic carbon burial, which in turn would affect atmospheric oxygen and CO2 levels. This is a classic if-then chain. If the planetary system is in a highly stable state, then it will resist change. But if a biological innovation is potent enough to alter the fundamental parameters of that system, then the system could be forced into a rapid, non-linear transition to a new state. This is the logic of tipping points. The billion years of stability may have been a period where the planet was slowly accumulating stress or enabling the evolution of the very things that would eventually break that stability. The quietness was not necessarily permanent, it was conditional. This introduces a sense of sensitivity without intent. The planet wasn't anticipating the future, the microbes weren't planning a revolution, but the system as a whole had a certain structure, a certain set of sensitivities. The long stability of the Proterozoic might have been the necessary preparatory phase for the Cambrian explosion of animal life that came much later. It was during this quiet time that the eukaryotes evolved and diversified, laying the genetic and metabolic groundwork. It was when the continental crust was stabilizing. It was when the fundamental biogeochemical cycles were being established. The system had to be built and calibrated before it could be pushed to the next level of complexity. So, the second-order effect of these feedback models is a profound reframing of the era. The stability was not a sign of stagnation, it was the signature of a robust, self-regulating system. And that very robustness, that deep equilibrium, created the predictable environment in which the biological tools for the next planetary transformation could be slowly and quietly forged. The quietness was the condition for the eventual noise. It's in moments like this, as we zoom from the planetary to the microbial and back again, that it's good to remember we are sharing this exploration. We are scattered all across the globe in different time zones, in rooms with different light and different air. But we are connected by this shared thread of curiosity. So, just for a moment, I invite you to check in with your own small corner of the planet. What time is it where you are? Is it deep night or early morning, or the middle of a busy afternoon? What is the weather like outside your window? Is it raining, or clear, or windy? This simple act of noticing your immediate environment is a way of anchoring this grand, abstract story in your own lived reality. The same fundamental forces that govern the Proterozoic Earth are operating right now, right where you are. The carbon cycle, the water cycle, the flow of energy from the sun. These are not just concepts in a script. They are the living processes that are creating the weather outside your window and sustaining the air you are breathing. You are situated inside this vast, ancient system. And if this journey is resonating with you, if it's sparking new questions or new ways of seeing the world, that is something we can share as well. If you feel so inclined, a simple thumbs up or a subscription is a quiet way of letting me know that these explorations are valuable. It's a small signal that helps this community of quiet curiosity find each other, but there's no pressure. The most important thing is simply that you are here, lending your attention to this story. Thank you for being here, wherever and whenever you are. Now, let's return to our ancient world. To build a robust model, we must not only present evidence for our view, but also fairly and honestly engage with the strongest counterarguments. This is the practice of steel manning, building the strongest possible version of the opposing case, not a weakened straw man that is easy to knock down. The mainstream explanation for the Proterozoic for a long time has been framed by that nickname, the boring billion. Let's steelman that argument. What is the evidence and the logic behind the idea that this era was one of genuine stagnation? The first and most powerful piece of evidence is the fossil record, or rather, the lack of it. For this vast stretch of time, from roughly 1.8 to 0.8 billion years ago, there is a striking absence of major biological innovations in the fossil record. We see evidence for the origin of eukaryotes near the beginning of this period, but then, not much seems to change. We find fossils of microbial mats, stromatolites, and microscopic fossils of single-celled organisms, acritarchs, but their diversity and complexity appear to remain remarkably constant for a billion years. There are no hints of multicellular animals, no complex algae, none of the biological fireworks that we see in the subsequent Ediacaran and Cambrian periods. If evolution is a story of constant change and diversification, then this billion-year-long chapter seems to be missing its plot. From a purely paleontological perspective, the boring label seems well earned. The world appears to have been stuck in a microbial holding pattern. The second line of evidence comes from geochemistry. Multiple chemical proxies in the rock record, such as the isotopes of carbon, sulfur, and molybdenum, suggest that the environment itself was incredibly stable. Most importantly, the evidence points to atmospheric oxygen levels being not only low, but also remarkably steady. After the initial rise during the Great Oxidation event, oxygen seems to hit a plateau and stay there. This environmental stasis is seen as the primary cause of the biological stasis. The argument is simple and powerful. Complex life, especially large mobile animals, requires high levels of oxygen to fuel its metabolism. Without sufficient oxygen, the evolutionary pathway to animal life was blocked. The world was simply not a permissive environment for that kind of biological complexity. The biosphere had hit a ceiling imposed by planetary chemistry. A third pillar of the boring billion argument centers on nutrient availability. Modern oceans are fertilized by nutrients like phosphorus and nitrogen, which fuel the base of the food web. There is geochemical evidence to suggest that the Proterozoic oceans might have been severely nutrient-limited. For example, some models suggest that the configuration of the supercontinent Columbia, with its vast, unweathered interior and potentially sluggish ocean circulation, could have led to a very low rate of nutrient supply to the shallow seas where life was most abundant. Without an adequate supply of these essential building blocks, biological productivity would have been chronically low. A nutrient-starved ocean cannot support a large or complex biosphere. Life was not just waiting for oxygen, it was also waiting for a decent meal. Putting these pieces together, the Steelman case for the boring billion is formidable. It's not just a casual nickname, it's a hypothesis grounded in multiple independent lines of evidence. The story it tells is one of constraint. Life, despite its inherent creativity, was trapped by a hostile and impoverished environment. The planet's biogeochemical systems were locked in a stable but unproductive state. Evolution had produced the eukaryotic cell, a revolutionary piece of biological hardware, but the world offered no opportunity to run any interesting new software on it. The billion years of quiet were not a period of hidden preparation, but a genuine, frustrating, and very long pause. The Earth was habitable, yes, but it was not yet hospitable to the kind of biological complexity that would one day lead to us. The quietness was the sound of a world waiting for a fundamental shift in its operating conditions. Now that we have presented the strongest case for the boring billion as a period of genuine stagnation, let's explore alternative interpretations. This is not about declaring one side right and the other wrong. It is about placing different models side by side, acknowledging that the same set of sparse and ambiguous evidence can often support multiple plausible narratives. The goal is to see the issue in 3 dimensions, preserving a sense of scientific humility and identifying the known unknowns that prevent us from making a final judgment. The first alternative interpretation reframes stasis as stabilization. This is the idea we've begun to develop. In this view, the constant fossil record and stable geochemistry are not signs of a system that is stuck, but of a system that is mature and well-regulated. A billion years is a very long time for an entire planetary system to remain in equilibrium. This suggests the presence of incredibly powerful negative feedback loops connecting life, climate, and geology. From this perspective, the boring billion was the most critical period in Earth's history for the development of long-term habitability. It was the era when the planet learned how to regulate itself, to maintain a stable climate despite a brightening sun and other perturbations. The quietness was not a failure of evolution, but the triumph of planetary-scale homeostasis. The main unknown here is the precise nature of those feedback loops. We can model them in the abstract, but identifying their specific geological and biological components is a major frontier in Earth science. A second alternative focuses on what we might be missing in the fossil record. Our understanding of Proterozoic life is based on a handful of fossil-bearing rock formations. The geological record is notoriously incomplete. It's entirely possible that significant evolutionary events were happening, but they were not preserved, or we simply haven't found the evidence yet. For instance, the earliest stages of multicellularity might not involve hard parts that fossilize easily. The first simple animals could have been microscopic, soft-bodied organisms that left no trace. Furthermore, key innovations might have been happening at the genetic and metabolic level. The boring period may have been a time of intense intracellular evolution within the eukaryotes, a time of software development, new gene, regulation networks, metabolic pathways, and cell-to-cell communication methods. In this view, the billion years were not a pause, but a period of deep cryptic innovation that was invisible in the macroscopic fossil record, but was essential for the subsequent explosion of visible complexity. We are left with a significant unknown. Can we find new geochemical or genetic techniques to uncover this hidden history? A third interpretation offers a middle ground. It accepts the reality of environmental constraints, like low oxygen and scarce nutrients, but it argues that these constraints did not halt evolution, but rather channeled it in specific directions. This view suggests that the Proterozoic was the great age of microbial innovation. Instead of evolving new body plans, life was evolving new metabolic pathways, new ways to survive in extreme environments, and new forms of microbial cooperation. The vast microbial ecosystems of this era might have been incredibly complex and sophisticated in ways that we, as macroscopic animals, find difficult to appreciate. The evolution of nitrogen fixation, complex sulfide metabolisms, and countless other biochemical tricks could have been the main event. In this model, the quietness was only quiet at our scale. At the microbial scale, it might have been a time of intense competition, innovation, and ecological complexity. The unknown here is how to reconstruct the dynamics of these ancient microbial ecosystems. The clues are locked away in the subtle isotopic signatures of rocks, a language we are still learning to decipher. So, here we have at least three competing interpretations. Standing side by side, was it stagnation due to environmental limits? Was it a crucial period of planetary stabilization? Or was it an age of hidden, cryptic innovation at the microbial and genetic level? The truth may well be a combination of all three. Perhaps the planetary system was stable, and this stability did constrain the evolution of large animals, but it also provided the perfect predictable arena for the slow, methodical work of intracellular and microbial evolution. By holding these interpretations in parallel, we avoid the trap of a simplistic narrative. We acknowledge the unknowns and respect the ambiguity of the evidence. The question shifts from, was it boring? To, what was the nature of the stability? What were its consequences, and what kind of evolutionary work can get done in a quiet world? At this point, it is essential to pause and turn the lens on ourselves. How do we know what we claim to know? And what are the inherent limitations of our methods for peering into a past so profoundly deep? Acknowledging the mechanics of discovery and the biases in our data is not a weakness. It is the foundation of credible science. It builds a more honest and durable understanding. Our primary window into the Proterozoic is the rock record. Geologists are detectives who read stories in layers of stone. The fundamental principle is simple. In an undisturbed sequence of sedimentary rocks, the oldest layers are at the bottom and the youngest are at the top. But the rock record is not a perfect book. It's a book from which most of the pages have been ripped out. The processes of plate tectonics, subduction, mountain building, erosion are constantly destroying and recycling the Earth's crust. The older the time period we want to study, the fewer rocks are left for us to examine. Rocks from 2 billion years ago are rare, and they have often been cooked, squeezed, and chemically altered, a process called metamorphism, over the intervening eons, smudging the original text. This is the first and most profound bias. survivorship bias. We only get to read the stories of the rocks that survived. Entire continents and ocean basins from that time have vanished without a trace. Our second set of tools involves geochemistry, the analysis of the chemical composition of these surviving rocks. By measuring the ratios of different isotopes, variants of elements like carbon, sulfur, or oxygen, we can infer things about the environment in which the rock was formed. For example, the ratio of carbon-12 to carbon-13 can tell us about the activity of photosynthetic organisms. This is incredibly powerful, but it has its limits. We are measuring a bulk signal from a tiny piece of rock that represents a single point in space and time. We then have to extrapolate that signal to make claims about the entire global ocean or atmosphere. It's like trying to understand the entire world's economy by looking at a single grocery store receipt. Furthermore, we have to assume that the fundamental chemical cycles operated in the same way they do today. This is the principle of uniformitarianism, but it's an assumption, and it might be flawed when applied to a world as alien as the Proterozoic Earth. This leads to the problem of detection limits. Our instruments can only measure things above a certain threshold. For example, when we say the atmosphere was low in oxygen, the data often can't distinguish between 1% oxygen and 0.1% oxygen. Both are simply low. But for an early organism, the difference between those two levels could be the difference between life and death. Our view of the past is blurry, constrained by the resolution of our tools. We see the big picture of major state changes like the Great Oxidation Event, but the subtler and perhaps more interesting fluctuations are often lost in the noise. Then there is the fossil record itself. Fossilization is an exceptionally rare event. Most organisms, when they die, are eaten or decay completely. To become a fossil, an organism must die in the right place, like a quiet basin with rapid sediment deposition, have the right kind of body, hard parts are better than soft parts, and the resulting rock must survive for 2 billion years and then be exposed at the surface for us to find. The odds are astronomically against it. This means the fossils we do find are a tiny, biased sample of the life that actually existed. The record is dominated by organisms that lived in specific, fossil-friendly environments and had resilient body parts. The absence of evidence in this context is not necessarily evidence of absence. By understanding these limitations, survivorship bias in the rock record, the extrapolation challenge in geochemistry, the detection limits of our instruments, and the profound incompleteness of the fossil record, we can hold our conclusions with the appropriate degree of humility. It doesn't mean we know nothing. It means that what we know is provisional and built on a foundation of inference. We are constructing the most plausible story from fragmentary clues. This awareness is crucial as we now reopen our main thread of inquiry. Every piece of evidence we discuss from here on out must be viewed through this lens of methodological caution. We are seeing a ghost, a faint outline of a world, and our task is to sketch it as honestly as we can, acknowledging the vast empty spaces that surround our pencil strokes. The language we use to describe the past is not a neutral vessel. Our words are laden with metaphors and assumptions that can subtly shape our inferences and colour our understanding. To build a clearer picture of the Proterozoic, we need to be conscious of our linguistic framing and, where necessary, replace imprecise or misleading language with more disciplined descriptions. One of the most common traps is the use of anthropomorphic verbs, attributing human-like intention or purpose to natural systems. We might say that life was trying to conquer the land, or that the earth wanted to find a stable state. This is a natural storytelling shorthand, but it is deeply misleading. Natural selection is a process of differential survival and reproduction, not a conscious striving toward a goal. A planetary system settles into a stable equilibrium, not because it seeks balance, but because the physics and chemistry of its feedback loops make that state a probable outcome. A more disciplined approach is to replace these verbs of intent with verbs of process and mechanism. Instead of life was trying to adapt, we can say organisms with traits better suited to the new conditions tended to survive and reproduce more successfully. Instead of the planet regulated its temperature, we can say negative feedback loops between weathering and climate acted to stabilize the temperature. This may seem like a subtle shift, but it is fundamental. It moves us from a narrative of purpose to a narrative of process. Another area for caution is our reliance on metaphors. We've used several already. The planet as a thermostat, geology as a book, DNA as code. These analogies are powerful tools for understanding because they connect a complex, unfamiliar idea to a simpler, familiar one. But every metaphor has a limit, and it's important to clarify where the analogy breaks down. For example, while a planetary thermostat creates a stabilizing feedback, it is not designed. It has no set point. The equilibrium temperature is an emergent property of the system itself. Similarly, while DNA carries information like code, it is not written by a programmer. It is constantly being edited, copied with errors, and tested by the unforgiving environment. When we use a metaphor, we must be explicit about its limits. We can say, it's a bit like a thermostat, in that it creates a negative feedback, but unlike a thermostat. This practice preserves the explanatory power of the analogy while preventing it from misleading us. The choice of adjectives also matters. Calling the era the boring billion is a prime example. The word boring is not a neutral descriptor. It is a judgment. It centers our human desire for novelty, and action as the measure of a world's significance. It implies a lack of importance. By replacing a loaded word like boring with more neutral descriptive terms like stable, quiescent, or homeostatic, we open up new avenues for interpretation. The quietness is no longer framed as a failure, but as a characteristic to be investigated. What were the mechanisms of that stability? What were its consequences? This shift in language is a shift in the scientific question itself. Finally, we must be careful with the language of causality. It is tempting to draw simple linear chains of cause and effect. The rise of oxygen led to the rise of eukaryotes. But in a complex system, causality is rarely so straightforward. It is often networked and bidirectional. Did the rise of oxygen allow for eukaryotes, or did the evolution of eukaryotes, with their more efficient, oxygen-consuming metabolism, create the ecological niche that pulled oxygen levels up? The answer is likely both. The two are coupled in a feedback loop. A more accurate way to frame this is to talk about co-evolution. The biosphere and the geosphere evolved together, each shaping the other. Instead of saying A caused B, it is often more accurate to say A and B created the conditions for each other to emerge. This discipline in language is not about being pedantic. It is about striving for clarity of thought. By being mindful of anthropomorphism, explicit about the limits of our metaphors, deliberate in our choice of descriptors, and nuanced in our description of causality, we can build a model of the past that is less distorted by our own modern biases and assumptions. It allows the alienness of this ancient world to stand on its own terms. To make the patterns we've discussed feel more concrete, let's walk through a specific scenario, applying the logic of our first evidence track, the human-scale sensory experience of this world. We'll use a second-person narrative to place you directly inside the scene, building a chain of cause and effect from the ground up. Imagine you're standing on a broad, flat expanse of what looks like reddish-brown sand. But it's not sand. It's a vast, wind-swept plain of regolith, the blanket of broken-down rock and dust that covers the landscape. You are on the coast of the supercontinent Colombia. The air feels thin. You take a breath, and it doesn't satisfy. The low oxygen level, perhaps just a few % of what you're used to, makes your head feel light and your muscles weak. The sun is high in a hazy, pale orange sky. Its light feels diffuse and strangely flat, lacking the sharp clarity of a blue sky day. The weak ozone layer offers little protection, and you can feel an unnerving intensity to the sunlight on your exposed skin, a harshness that speaks of high ultraviolet radiation. There is no soil beneath your feet, not in the way we know it. There are no plants, no grasses, no trees. The land is utterly barren, a mineral landscape of rock, gravel, and dust, sculpted by wind and the occasional flash flood. There is no scent of vegetation or damp earth on the wind. The air smells of dust and a faint, sharp tang of ozone created by lightning splitting the nitrogen-rich air. The world is silent except for the whisper of the wind moving across the plains and the distant low roar of the sea. You walk toward that sound, As you approach the coastline, the landscape changes. You see broad, muddy tidal flats, crusted with salt in some places. And in the shallow water of the intertidal zone, you see the first clear sign of life. Stretching for miles along the coast are low, lumpy domes of layered rock. These are stromatolites. They are living structures, built by immense communities of cyanobacteria. The top layer is a greenish-black film of living microbes, performing photosynthesis in the harsh sunlight. Below that are layers of trapped sediment and calcium carbonate, the record of years, centuries, millennia of microbial growth. This is the dominant ecosystem on the planet, a city of bacteria. You look out at the ocean. As we established, it is not blue, but a pale, milky green. This is the direct consequence of its chemistry. Rivers washing off the barren continent carry a heavy load of dissolved iron into the sea. In this low-oxygen world, the iron remains in its soluble ferrous form, Fe2+, tinting the water. Now, watch what happens. As the waves lap against the shore, the highly oxygenated water, from the very surface layer, where the cyanobacteria are most active, mixes with the iron-rich water from slightly deeper. A chemical reaction occurs. The iron hits the oxygen and instantly rusts, turning into insoluble ferric iron, Fe3+. Tiny particles of iron oxide, rust, cloud the water, then slowly begin to settle out. This is the engine of the world in miniature. The sun powers the cyanobacteria. The cyanobacteria produce oxygen. The oxygen hits the iron delivered by the rivers. The result is a slow, continuous rain of rust onto the seafloor. Over millions of years, this process will build up the vast banded iron formations, the very rocks that now provide the evidence for the world you are witnessing. You are watching a planet-spanning chemical process unfold in a single wave. The chain of causality is clear. The sun's energy, fainter than today's, is captured by life. Life's waste product, oxygen, fundamentally alters the planet's chemistry. That chemistry dictates the color of the sky and the sea. The geology of the supercontinent dictates the flow of minerals that fuel these reactions. Each part of the system is linked. The sensory experience, the thin air, the orange sky, the green sea, the silent, barren land, is not a collection of independent facts. It is the single, coherent expression of a planet operating under a set of rules profoundly different from our own. Now let's shift our perspective and apply the logic of our second evidence track, the one focused on systems and feedbacks, to a contrasting scale. We'll move from the immediate sensory experience of a single location to the vast, interconnected dynamics of the entire planet over a much longer timescale. This requires us to think in terms of budgets, flows, and balances, quantifying where we can, to grasp the scale of the processes involved. Imagine you are looking at the Earth from space, 2 billion years ago. The first thing you'd notice is the geography. The supercontinent Columbia dominates one hemisphere, a vast reddish-brown landmass. The other hemisphere is a massive superocean. This simple geographic arrangement has profound consequences for the planet's climate and chemistry. The sheer size of the continent means its interior is far from the ocean's moderating, moisture-bearing influence. This creates a harsh continental climate, extremely hot and dry in the interior, with rainfall concentrated along the coasts. Now, let's look at the planet's energy budget. The sun is about 15 to 20% fainter than it is today. All else being equal, this would mean a frozen planet. Yet the geological evidence suggests that liquid water was abundant. This is the faint young sun, paradox. The solution must be a more powerful greenhouse effect. The atmosphere must have contained a higher concentration of greenhouse gases, carbon dioxide and likely some methane, to trap more of the sun's heat and keep the planet warm. Here is where the feedback loops kick in. Let's trace the carbon cycle, the planet's main thermostat. The primary source of CO2 is volcanism, which releases gases from the Earth's interior. The primary sinks are, first, the weathering of silicate rocks on land, and second, the burial of organic carbon in the oceans. In our Proterozoic world, the weathering sink would be relatively inefficient. Without land plants to break up rocks, the process would be slow. This means that to achieve a balance, the biological sink, the burial of organic carbon, must have been incredibly important. Let's put some rough numbers on it. Photosynthesis was drawing down CO2 and producing oxygen. Let's call the total amount of oxygen produced gross primary production. However, most of this oxygen was immediately consumed by the respiration of other microbes that ate the organic matter. Only a tiny fraction of the organic matter produced, perhaps less than 0.1%, escaped being eaten and was buried in sediments. It is this small buried fraction that corresponds to the net addition of oxygen to the atmosphere. For oxygen levels to remain stable, this net addition must be perfectly balanced by the oxygen sinks, the rusting of minerals on land and in the sea, and the reaction with volcanic gases. This creates a system that is powerfully regulated but operating at a low level. Imagine a bathtub with the faucet barely open, and a drain that is exactly the right size to let out water at the same rate. The water level in the tub will be low, but it will be very stable. This was the Proterozoic oxygen system. The faucet, net oxygen production via carbon burial, was only slightly open, and the drain, the vast planetary oxygen sinks, was perfectly matched to it. Now consider the scale shift. We saw iron rusting in a single wave on the shore. From our macro perspective, we see that this process, happening along thousands of miles of coastline for millions of years, is a critical part of the planetary drain for oxygen. A small, local event, when integrated over geological time and space, becomes a globally significant parameter in a feedback system. The existence of the supercontinent influences the rate of nutrient runoff, which controls the rate of photosynthesis, which determines the size of the faucet. The planet's internal heat engine drives volcanism, which helps set the size of the drain. This view reveals the quietness of the era, not as an absence of activity, but as the signature of a tightly balanced system. The inputs and outputs were small, but they were in equilibrium. It was a world of low power, but high stability. The microscale chemistry of a single microbe multiplied by trillions and integrated over an eon created a planetary state. The contrast is clear. In the first case template, we saw the results of the system's chemistry on a human scale. In this second template, we see the vast, slow-moving mechanisms that maintain that chemistry on a planetary scale. Let's introduce another powerful piece of evidence, a macro-scale driver that shaped the very rhythm of this ancient world, the Earth-Moon coupling. This is a story of gravity, tides, and the slow exchange of angular momentum. It operated in the background, a silent but potent force that influenced everything from the length of a day to the dynamics of coastal ecosystems. 2 billion years ago, the Moon was significantly closer to the Earth. The laws of orbital mechanics tell us that the Moon has been slowly receding from the Earth over its entire history, a process that continues today at a rate of about 3.8 centimeters per year. Extrapolating backward, while accounting for changes in tidal forces, scientists estimate that the Moon was perhaps only 320,000 kilometers away, compared to its average distance of about 384,000 kilometers today. This might not sound like a dramatic difference, but the effect of gravity diminishes with the square of the distance, and tidal forces diminish with the cube of the distance. A closer Moon means much, much stronger tides. The gravitational pull of this closer Moon would have had a profound effect on the Earth's rotation. The friction generated by the tides, the daily sloshing of the oceans back and forth, acts as a brake on the planet's spin. This process is called tidal friction. It converts the Earth's rotational energy into heat, slowing the planet down. At the same time, to conserve angular momentum in the Earth-Moon system, the Moon is pushed into a higher orbit, moving farther away. This is the mechanism for its recession. The consequence of a faster transfer of momentum in the past is that the Earth was spinning much faster. A day was not 24 hours long. The best estimates for 2 billion years ago place the length of a day at around 19 to 20 hours. Let's pause to consider the implications of this. A shorter day means a different world. The sun would have appeared to move more quickly across the sky. The cycle of light and dark, the most fundamental rhythm for photosynthetic life, would have been accelerated. Organisms would have had less time to photosynthesize during the day, which might have had a direct impact on their productivity and, by extension, the entire planet's oxygen budget. The tides themselves would have been monstrous by modern standards. The difference between high and low tide could have been tens of meters in some basins, creating immense intertidal zones, vast areas of land that were submerged at high tide and exposed at low tide twice per day. This would create a unique and highly dynamic environment. The constant, powerful flushing of these tidal flats with nutrient-rich water could have made them incredibly productive hotspots for microbial life. The vast stromatolite reefs we imagined earlier would have thrived in this high-energy environment, their growth patterns potentially even recording the rhythm of these ancient tides. This process of rotational damping also had a crucial effect on the planet's climate stability. The Earth's spin acts like a gyroscope, stabilizing its orientation in space. The Moon's gravity, pulling on the Earth's equatorial bulge, also helps to stabilize the planet's axial tilt, the 23.5-degree angle that gives us our seasons. Without the Moon, the gravitational influence of Jupiter and other planets would cause Earth's tilt to vary chaotically over millions of years, leading to wild and catastrophic swings in climate. The presence of a large, close moon was a critical stabilizing force, preventing these extreme variations and helping to maintain the long-term climate stability that characterized the Proterozoic. So, the Earth-Moon coupling represents another powerful planet-scale mechanism. It is not biological or chemical, but physical and gravitational. Yet it is deeply intertwined with the other systems we've discussed. The strength of the tides would have depended on the shape of the ocean basins, which was determined by the configuration of the supercontinent. The productivity of life in the intertidal zones, driven by these massive tides, would have influenced the global carbon and oxygen cycles. The length of the day would have constrained the daily energy budget of photosynthetic organisms. And the stability of the climate, guaranteed by the Moon's steadying hand, provided the predictable backdrop against which the slow drama of planetary regulation and early evolution could unfold. This is a beautiful example of how forces from beyond our planet can reach down and shape the very fabric of life and geology upon it. The consequences of this tight planetary coupling with a closer moon extend beyond the simple mechanics of tides and day length. They touch upon the very definition of planetary habitability. When we think about what makes a planet habitable, we usually focus on factors like its distance from its star and the presence of liquid water. But the evidence from our own deep past suggests that the story is far more complex. The long-term stability of a planet's climate may be just as important as its surface temperature at any given moment. Let's translate the abstract physics of the Earth-Moon system into the language of lived time for the biosphere. The Moon's gravitational influence acted as a planetary anchor, damping the chaotic swings in axial tilt that would have otherwise occurred. What would such swings have meant? Imagine a world where over a few million years, the planet's tilt shifts from 23 degrees to 60 degrees. The poles would receive more direct sunlight than the equator. The very concept of tropics and Arctic regions would break down. The climate would be thrown into a state of violent, unpredictable flux. Ice caps could form at the equator and then melt away as the tilt shifted back. Such a world would be subject to relentless, catastrophic climate change on geological timescales. It would be incredibly difficult for complex life to evolve in such an environment. Evolution works by adapting to a given set of conditions. If those conditions are constantly and radically changing, it's like trying to build a house in the middle of a perpetual earthquake. The Proterozoic Earth, however, was not like this. Thanks to the stabilizing presence of the Moon, the planet's seasons and climate zones were predictable over very long periods. This provided a stable canvas on which evolution could work. It allowed for the development of those robust, self-regulating biogeochemical cycles we've been discussing. The systems that maintained the low oxygen equilibrium were able to establish themselves because they weren't being constantly disrupted by catastrophic climate shifts. This has profound implications for our search for life elsewhere. We may need to look for not just Earth-like planets, but for planets with Earth-Moon-like systems. A large moon might be a critical and perhaps rare ingredient for long-term habitability and the eventual evolution of complex life. A planet might be in the habitable zone of its star, but if it lacks a large moon to stabilize its spin axis, it might be a world of such violent climate swings that it can never move beyond a simple microbial biosphere. Now, Let's bring this back to the shorter 19-hour day. This faster rotation would have also had a significant impact on climate and weather. The Coriolis effect, the force that creates the swirling patterns of hurricanes and ocean currents, is stronger on a faster spinning planet. This would have led to a more banded atmospheric circulation, perhaps more like Jupiter's, with stronger and more stable jet streams. Weather systems might have been smaller but more intense. The transfer of heat from the equator to the poles would have been different. These are all critical parameters of the climate system. By translating the gravitational coupling into these consequences, we see how an astronomical feature can become a biological and geological one. The presence of the moon was not just a passive fact about the sky. It was an active participant in the Earth system. It helped create the stable, predictable environment in which the quiet, methodical work of the Proterozoic could take place. It protected the nascent biosphere from climatic chaos. The very quietness and stability we have been working to understand was, in part, a gift from our celestial neighbour. The long, boring billion years may have only been possible because the moon was there, holding the Earth steady. How do we read a history with so few written pages? Our next evidence track explores the concept of archives, the ways in which the Earth system records its own past. These are not perfect records. They are smudged, incomplete, and often difficult to decipher. But by understanding the nature of these archives, we can learn to read the faint signals they contain. The primary archive for deep time is sedimentary rock. Imagine a large, quiet body of water, perhaps a basin on the continental shelf of Colombia. Over time, sediment, particles of clay, silt, and sand from the erosion of the continent, along with the organic remains of microbes, slowly settles to the bottom. Year after year, century after century, new layers are added on top of the old ones, creating a vertical stack of history. This stack, when compressed and hardened into rock, becomes a physical timeline. This is a sedimentary sequence. It is, in a very real sense, a memory of the world in which it was formed. What kind of information is stored in this archive? The physical characteristics of the layers, the size of the grains, the presence of ripple marks, can tell us about the energy of the environment. Was it a quiet, deep water setting, or a high-energy coastal zone? But the real treasure lies in the chemical information locked within the minerals and the trapped organic matter. Geochemists are the librarians of this ancient archive. They can drill a core through these layers and read the story, page by page, layer by layer. For example, by measuring the isotopes of carbon, they can track the productivity of the biosphere. Photosynthesis preferentially uses the lighter isotope carbon-12, so when a layer of sediment is rich in organic matter that is isotopically light, it signals a time of high biological productivity. By measuring sulfur isotopes, scientists can infer the extent of anaerobic processes in the ocean, giving us clues about the level of oxygenation. By analysing trace metals like molybdenum and vanadium, whose solubility depends on the presence of oxygen, we can further constrain the chemistry of the water column. The banded iron formations we've discussed are a particularly dramatic example of this archival process. They are thick sequences of rock with alternating layers of iron-rich minerals like hematite and magnetite, and silica-rich minerals, chert. Each band can be thought of as a record of a change in local ocean chemistry, likely driven by pulses of oxygen production from cyanobacteria. Reading these formations is like reading a barcode of the ancient ocean's oxygenation state. However, a key feature of any archive is that it records events with a delay. It's a lagging indicator. The chemical signal found in a rock reflects the conditions in the ocean at the time of its deposition. But those ocean conditions were themselves a result of processes happening over vast areas and long timescales. A change in the global atmosphere might take thousands of years to be fully reflected in the chemistry of the deep ocean and then recorded in the sediment. This means the sedimentary archive is a smoothed-out, low-resolution version of history. It's good at recording long-term trends and major state shifts, but it's poor at capturing rapid, short-term events. The billion years of stability we see in the geochemical record might be real, or it might be an artifact of this smoothing process, where short-lived fluctuations are averaged out over time. Furthermore, the archive is constantly being edited and erased. The process of turning sediment into rock, lithification, can alter its chemical signatures. Later metamorphism can almost completely overwrite them. This means that the farther back in time we go, the more degraded the archive becomes. We have to learn how to read through this degradation to find the chemical signals that are robust enough to survive billions of years of geological processing. Thinking of the Earth as an information processing system with a geological memory is a powerful metaphor. It highlights both our ability to know and the limits of our knowledge. We are not just looking at rocks. We are trying to decode a message sent to us from an impossibly distant past. The message is faint, it is fragmented, and it is written in a language of isotopes and minerals that we are only just beginning to fully understand. The quietness of the Proterozoic is partly a feature of the world itself, but it is also a feature of the archive that recorded it, an archive that specializes in preserving the slow, the steady, and the long-term. Given the nature of this sedimentary archive, its incompleteness, its low resolution, and its inherent biases, what can we confidently infer, and what remains beyond our grasp? Understanding the constraints of our data is as important as understanding the data itself. This is about establishing confidence bands around our reconstruction of the past. First, what can we infer with high confidence? The broad strokes of the Proterozoic world are well established because they are supported by multiple independent lines of evidence from archives all over the world. We can be very confident that atmospheric oxygen levels were significantly lower than they are today. The disappearance of certain easily oxidized minerals like pyrite from riverbed deposits and the widespread existence of banded iron formations provide a clear and unambiguous signal of a low-oxygen world. We can also be confident that the oceans were chemically stratified with anoxic, iron-rich deep waters. The isotopic systems of various metals that are sensitive to oxygen confirm this picture repeatedly. Furthermore, we can be confident that life was overwhelmingly microbial. The fossil record, despite its patchiness, consistently shows a world of stromatolites and microscopic single cells without any credible evidence for animals until much, much later. These fundamental features of the Proterozoic landscape are robust. They are not the result of a single measurement, but a consensus that has emerged from decades of work on countless different geological archives. Now, what can we infer with moderate confidence? We can be reasonably sure that a supercontinent, Columbia, existed and that the day was shorter. The evidence for this comes from paleomagnetism, which tells us the past positions of continents, and from geological models of tidal friction, but the exact shape of the supercontinent and the precise length of the day are still subjects of active research and debate. The numbers we use are best fit estimates from models, not direct measurements. Similarly, we can be moderately confident that the long period of stability seen in the carbon isotope record is a real feature of the Earth system. The signal is so consistent across so many different locations that it's unlikely to be a complete artifact of the archive. However, the degree of that stability is less certain. As we discussed, the archive smooths the data, so it's possible that this long, flat line hides a great deal of higher frequency variability that our current methods cannot resolve. Finally, what are the things we simply cannot infer with any confidence from the archival signals? We cannot know the specifics of microbial ecosystems. The rocks can tell us that photosynthesis was happening, but they can't tell us about the complex food webs, the competitive and cooperative interactions, or the ecological dynamics of the microbial communities that drove it. We cannot know the true diversity of early eukaryotic life. The few microfossils we have are like a handful of snapshots from a billion-year-long movie. They give us a glimpse, but they cannot tell us the whole story of their evolution. Most importantly, we cannot infer the why behind the stability with certainty. We can build plausible models of feedback loops as we have done, but the sedimentary record can't definitively prove that one particular mechanism was the dominant one. It can only provide circumstantial evidence that is consistent with those models. This process of sorting our knowledge into confidence bands is crucial. It prevents us from overstating our case. It allows us to say, here is what we know for sure, here is what we think is likely, and here is where we are still speculating. It defines the frontier of our ignorance, and in doing so, it points the way for future research. The story of the Proterozoic is not a finished book. It's a manuscript with many chapters yet to be written. The archival signals have given us the outline of the plot, but the details, the character motivations, and the subplots are still waiting to be discovered in the faint ink of the geological record. We have now journeyed through several distinct tracks of evidence, from the sensory scale of a single coastline to the gravitational dance of the Earth-Moon system, and finally to the very nature of the geological archive itself. We've touched on chemistry, biology, geology, and planetary science. Before we move forward, let's pause. We are approaching the midpoint of our exploration. Soon we will begin to synthesize these disparate threads into a more unified, dynamic model of this ancient world. We will move from gathering clues to building a coherent theory of the case. We will explicitly address the strongest criticisms and then attempt to reframe the entire boring billion concept, not as a period of stasis, but as a period of profound and necessary preparation. This coming synthesis will require us to hold all the threads we've gathered so far in our minds at once. The low oxygen air and green seas, the powerful regulating feedbacks, the stabilizing presence of the closer moon, the constant rain of rust onto the seafloor, and the patchy, incomplete nature of the very record we are reading. We will try to see how these pieces lock together, how they constrain and influence one another. Think of this as a promise. We have laid out the pieces of the puzzle. The next phase of our journey is to start fitting them together, to see what picture begins to emerge when we view the system as a whole. The quietness of this world, which we first posed as a simple, elegant question, will reveal itself to be a complex and multifaceted phenomenon, a product of a remarkable planetary scale conspiracy of stability. For now, just let these ideas settle. The synthesis is yet to come. Let's add another layer of complexity to our model, another crucial evidence track that highlights the deep and intimate connection between life and the planet. This is the conversation between the biosphere and the atmosphere, the way that ecosystems can actively shape their own weather and chemistry through a series of subtle but powerful feedback loops. In the Proterozoic, this conversation was dominated by the planet's vast microbial mats. Imagine those endless stretches of stromatolites in the shallow coastal zones. These were not just passive inhabitants of their environment, they were ecosystem engineers. The surface of these mats was a complex, multi-layered community of different microbes. The top layer, exposed to sunlight, was dominated by our familiar friends, the cyanobacteria, producing oxygen. But just millimeters below the surface, in the anoxic layers, lived a whole different suite of microbes, including sulfate-reducing bacteria. These organisms respired using sulfate instead of oxygen, and a key byproduct of their metabolism was a gas called dimethyl sulfide, or DMS. In our modern oceans, DMS produced by plankton is a crucial player in the climate system. When DMS is released into the atmosphere, it oxidizes to form tiny sulfate aerosol particles. These particles act as cloud condensation nuclei, the microscopic seeds around which water vapor can condense to form cloud droplets. More DMS means more cloud seeds, which means brighter, more reflective clouds. These bright clouds, in turn, reflect more sunlight back into space, which has a cooling effect on the planet. This is a potential negative feedback loop. If the planet gets warmer, plankton activity might increase, releasing more DMS, creating more clouds, and cooling the planet back down. This is part of a theory known as the CLAW hypothesis. Could a similar process have been at work in the Proterozoic? It's highly plausible. The microbial mats in the vast shallow seas would have been prodigious producers of DMS. This could have represented another powerful biologically mediated climate thermostat, working alongside the geological carbonate-silicate cycle. It's another example of homeostasis emerging from the undirected metabolic activity of life. The microbes are not trying to regulate the climate, they are simply living, and the chemical byproducts of their lives happen to have a profound effect on the atmosphere. It's crucial that we depersonify this process. There is no intent, only consequence. The biome and the atmosphere are locked in a chemical conversation, a continuous exchange of matter and energy that shapes the entire Earth system. This conversation wasn't limited to just clouds and climate. The presence of the biosphere fundamentally altered the planet's chemistry. Consider the nitrogen cycle. Nitrogen is an essential nutrient for life, but the abundant nitrogen gas, N2, in the atmosphere is unusable by most organisms because of its strong triple bond. A process called nitrogen fixation, carried out by specialized microbes, is required to convert N2 into a usable form like ammonia. These nitrogen-fixing microbes were a critical component of the Proterozoic ecosystem. Without them, the entire biosphere would have been starved of this vital nutrient. The global rate of nitrogen fixation, controlled by microbes, thus placed a fundamental limit on the total amount of life the planet could support. Here we see another coupled system. The availability of other nutrients, like phosphorus, which comes from the weathering of rocks, would influence how much microbial growth could occur. This growth would then determine the demand for nitrogen, driving the activity of the nitrogen fixers. The entire nutrient economy of the planet was being managed and mediated by this complex microbial consortium. By looking at these biome-atmosphere conversations, our picture of the Proterozoic becomes much more dynamic. It's not just a story of geology imposing limits on life. It's a story of life actively participating in the creation of its own environment. The stability of the era arises not just from passive geological feedbacks, but from these active, biologically mediated loops. The planet was not a static container for life. The planet and the biosphere were a single, deeply integrated, co-evolving system. The long quiet of the Proterozoic was the sound of this conversation settling into a steady, predictable rhythm. A system governed by powerful feedback loops is resilient, but it is not invincible. Every such system has thresholds, tipping points beyond which the regulating mechanisms can fail or flip into a new state. Understanding the resilience, thresholds, and potential failure modes of the Proterozoic Earth system is key to understanding why the boring billion eventually came to an end. Let's consider the oxygen regulation system again. We pictured it as a bathtub with a small, steady inflow and a perfectly matched drain. This system is resilient to small disturbances. If there's a slight increase in the inflow, a temporary bloom of cyanobacteria, the big drain, the vast reservoir of reducing compounds in the ocean, and rocks can easily handle it, and the water level remains stable. This is the essence of the Proterozoic stability. The oxygen sinks were so enormous that they could buffer any plausible increase in oxygen production. The system was locked in a low oxygen state. So what could cause this loop to fail? There are two main possibilities. You could dramatically increase the inflow, or you could somehow plug the drain. Let's think about the drain first. The primary oxygen sink was the dissolved iron and other reducing species in the deep ocean, supplied by hydrothermal vents and continental weathering. Over 1 billion years, the constant slow rain of rust driven by oxygen from the surface was gradually cleaning up this sink. The deep ocean was slowly, almost imperceptibly being titrated. This was a process operating on an immense timescale. For hundreds of millions of years, it would have no noticeable effect. But eventually, after a vast amount of time, the reservoir of sinks would begin to shrink. The drain was slowly getting smaller. Now think about the inflow. What could cause a dramatic, sustained increase in oxygen production? This would likely require a major biological innovation or a significant geological change. For example, the evolution of the first true algae, eukaryotic photosynthesizers, might have been much more efficient at producing and exporting organic carbon to the deep sea than their bacterial predecessors. This would increase the rate of carbon burial, and therefore the net production of oxygen. Or a major episode of continental breakup and mountain building could have dramatically increased the supply of key nutrients, like phosphorus, to the oceans. This would act as a fertilizer, leading to a global surge in biological productivity. Here we see the logic of a tipping point, but without the drama. It's a slow geological process. For 1 billion years, the system is stable because the sinks are larger than the sources. But all the while, the sources are subtly evolving, biological innovation, and the sinks are subtly shrinking, geological titration. At some point, the balance inevitably shifts. The inflow begins to consistently overpower the drain. At this point, the system crosses a threshold. The deep oceans can no longer absorb all the oxygen being produced, and free oxygen begins to accumulate rapidly in the deep sea and the atmosphere. The bathtub, which has been held at a low, stable level for an eon, suddenly begins to fill up. This is not a failure in the sense of something breaking. It's a state transition. The system is pushed out of one stable equilibrium and into a new one, in this case, a high-oxygen world. This transition would likely have been catastrophic for much of the incumbent anaerobic and low-oxygen adapted life, but it also opened up vast new ecological and energetic possibilities. The high-energy lifestyle of animals is only possible in a high-oxygen world. The failure of the old Proterozoic system was the necessary precondition for the success of the new Phanerozoic system that includes us. Understanding these failure modes helps us see the boring billion in a new light. It wasn't a permanent state. It was a long, stable chapter in the planet's history, but it was a chapter that had a built-in ending. The very processes that maintained the stability, the slow, continuous burial of carbon and rusting of the deep oceans, were also the processes that were inexorably leading to its eventual demise. The quietness contained the seed of the future noise. To grasp the nature of life in this era, particularly the monumental leap from simple prokaryotic cells to more complex eukaryotic cells, it can be helpful to use an analogy from a more familiar world, the world of computers. We can think of the evolution of life as the development of a planetary-scale biological operating system. But, like all analogies, this one must be used with explicit and important caveats. In this analogy, the simple prokaryotic cells, like bacteria, are like early command-line computer programs. They are incredibly efficient, robust, and specialized for specific tasks. A nitrogen-fixing bacterium is like a perfect, tiny utility that does one thing exceptionally well. For over 1 billion years, the planet's operating system was a distributed network of these single-purpose applications. It was powerful and resilient, but not very flexible. The emergence of the eukaryotic cell, through the process of endosymbiosis, was a fundamental upgrade to the hardware and the operating system. It was like moving from DOS to Windows or Mac OS. Suddenly, you have a graphical user interface. You have specialized components working together within a single integrated architecture. The cell's nucleus acts like a central processing unit, protecting and managing the core code, the DNA. Other organelles, like the Golgi apparatus and the endoplasmic reticulum, are like specialized hardware for manufacturing and shipping products. And most critically, the eukaryotic cell acquired its own power plant, the mitochondrion. Mitochondria are the descendants of free-living bacteria that were engulfed by an ancestral host cell and became permanent residents. This was a revolutionary moment. Mitochondria are incredibly efficient at using oxygen to generate energy. A eukaryotic cell can produce far more energy than a prokaryotic cell of the same size. This massive increase in available energy, this new power supply, is what opened the door to all future complexity. It allowed cells to become much larger, to build more complex internal structures, and eventually to cooperate in the vast multicellular projects that are plants and animals. Now for the crucial caveats. Unlike a computer operating system, this biological OS was not designed by an intelligent engineer. It was cobbled together through billions of years of random mutation and natural selection. It is a product of historical contingency, not deliberate planning. There is no top-down blueprint. The code in DNA is not neatly organized and commented like human-written software. It is messy, redundant, and full of relics from its evolutionary past. And finally, the system is not running on a stable, inert piece of hardware. The computer is the planet itself, and its own geological evolution is constantly changing the rules and the available resources. The hardware and the software are co-evolving. Despite these caveats, the analogy is useful because it helps us frame the significance of the Proterozoic. The boring billion can be seen as the long period of debugging and optimizing this new eukaryotic operating system. The basic hardware, the eukaryotic cell with its mitochondria, was in place. But it took another 1 billion years to develop the software, the genetic toolkits for cell-to-cell communication, for cell adhesion, for differentiation into specialized types. That would be necessary to build the first multicellular organisms. This was not a period of stagnation. It was a period of intense cryptic innovation happening at the level of the genome and the cell. The world was quiet on the outside, but on the inside of these new eukaryotic cells, a revolution was brewing. The foundational code for the entire animal kingdom was being written, one line at a time. This framing of biology as code leads to a more nuanced understanding of biological systems, moving away from a language of perfection and toward a language of robustness and resilience. The systems that emerge from evolution are not perfectly designed. They are good enough to survive and reproduce in their given environment. This distinction is crucial for understanding the nature of life during the Proterozoic and why it was able to persist through such vast stretches of time. A system designed for perfection is often brittle. It works flawlessly under a specific set of conditions, but it can fail catastrophically if those conditions change even slightly. Think of a high-performance racing engine. It is a marvel of engineering, but it requires a specific type of fuel, a narrow temperature range, and constant maintenance. It is not robust. In contrast, an old tractor engine is a model of robustness. It might not be the most efficient or powerful, but it will run on low-quality fuel, tolerate a wide range of conditions, and keep working even when some of its parts are worn out. Evolutionary systems are much more like the tractor engine than the racing engine. The eukaryotic cell is a prime example. It is not a perfect, streamlined design. It is a messy coalition of once-independent organisms cobbled together by historical accident. Its genome is full of non-coding junk DNA and ancient viral insertions. Yet, it is this very messiness that can contribute to its resilience. This genetic redundancy can provide the raw material for future evolutionary innovations. A seemingly useless gene, duplicated millions of years ago, might be repurposed to perform a new and vital function when the environment changes. This concept of graceful failure is also key. A robust system doesn't just suddenly collapse when it is stressed, it degrades gracefully. The Proterozoic biosphere, with its powerful regulating feedbacks, was likely very good at this. When faced with a stressor, like a pulse of volcanic gases that drew down oxygen, the system didn't just die. Parts of it might have suffered, but the overall structure would have remained intact, ready to bounce back when conditions improved. The stability of the era was a testament to this incredible resilience. This reframes our view of the boring billion. It was not a time when life was failing to achieve perfection. It was a time when life was honing its ability to be robust. It was developing the deep systemic resilience that would allow it to survive future crises. From global glaciations, snowball Earth events, to massive asteroid impacts, the long period of environmental stability may have been the perfect training ground for building this resilience. It allowed for the slow, methodical process of testing and refining the systems that allow life to persist in a dangerous and unpredictable universe. The adaptive systems that emerged were not flawless, but they were durable. The eukaryotic operating system was not a sleek, minimalist piece of code. It was a sprawling, patched-together legacy system, but it was a system that worked, and one that contained the latent potential for immense future complexity. The quietness of the era was not the quiet of a system waiting for a perfect solution. It was the quiet hum of a system that had found a good enough solution, and was reinforcing it, strengthening it, and embedding it into the very fabric of the planet, preparing it for the challenges to come. To truly grasp the alienness of this Proterozoic world, we need to reconstruct a landscape that no longer exists, the heart of a supercontinent. Let's use our final evidence track to travel to the interior of Colombia, 1 billion miles and 2 billion years from the familiar coastlines we've already visited. This is a journey into a world defined by immense scale and profound emptiness. We start our journey on the coast, amidst the familiar green seas and stromatolite reefs. We move inland. For the first 100 miles or so, we might be in a region of monsoonal rains, where seasonal downpours carve deep channels into the rock and feed vast, shallow, ephemeral lakes. Here, microbial mats might still find a foothold, clinging to life in the wet seasons. But as we press deeper into the continent's interior, the influence of the ocean fades, and the world becomes progressively drier and more sterile. Hundreds of miles from any ocean, the landscape is a panorama of staggering monotony. Vast, flat plains of wind-scoured rock and reddish, iron-rich dust stretch to every horizon. There are no hills or mountains, just the gentle, almost imperceptible, curvature of the Earth. The supercontinent was formed from the collision of earlier continents, but by 2 billion years ago, The mountain ranges that were thrown up by those collisions would have been eroded down to their very roots, leaving a flat, stable continental core, a craton. The sun beats down from the hazy orange sky with a relentless, unfiltered intensity. The temperature here would be extreme. With no oceans to moderate the climate and no plant cover to retain moisture, the daily temperature swings could have been enormous, scorching hot during the long 19-hour day and plunging to bitterly cold temperatures at night. The air is bone dry. Rain might not fall in this region for centuries at a time. It is one of the largest and most extreme deserts the planet has ever known. What breaks the monotony? Perhaps a vast, slow-moving river, its headwaters thousands of miles away, in a coastal mountain range we cannot see. Its braided channels would be the only sign of water, its banks encrusted with salt and other evaporate minerals. This river would not be teeming with life. It would be a sterile, mineral-rich flow, carrying the crushed-up remains of a continent out to the distant sea. The only other features are the products of the wind, huge fields of sand dunes, composed not of quartz sand like today's deserts, but of reddish, iron-stained dust, would migrate slowly across the landscape. Dust storms, larger than any we know today, could rage for weeks, obscuring the faint sun and choking the thin atmosphere. And there is the silence, a silence more profound than any on Earth today. There are no insects, no birds, no rustling leaves. There is only the sound of the wind, the hiss of blowing dust, and the occasional crack of a rock fracturing under the thermal stress of the daily temperature swing. It is the sound of pure geology. This is a world almost entirely without biology. Life has not yet conquered the continents. It is a thin, green fringe clinging to the edges of this vast, dead heartland. Rebuilding this unfamiliar world is essential because it underscores the true scale of the Proterozoic planet. The biosphere was small and marginal. The vast majority of the land surface was sterile. This has major implications for global chemical cycles. The weathering of this huge exposed landmass would proceed very differently without the influence of plants and soil microbes. The amount of dust blown from these deserts into the ocean would have been immense, and this dust could have been a key source of nutrients like iron to the marine biosphere. The sterile heart of the supercontinent was not disconnected from the living world. It was the slow geological engine that supplied the raw materials for the thin coastal film of life. This stark, empty landscape is a crucial piece of our puzzle. The existence of a supercontinent like Columbia is not just a geographical curiosity. It is a fundamental driver of the entire planetary system, with profound consequences for global climate and the distribution of life. The harsh, arid interior we just imagined is a direct result of what is known as the continental interior effect. Moisture in the atmosphere largely comes from evaporation off the surface of the ocean. Winds carry this moisture over land, where it eventually falls as rain or snow. In our modern world, with its scattered, smaller continents, most land areas are relatively close to an oceanic source of moisture. But a supercontinent creates a problem of scale. The very center of a landmass the size of Columbia would have been thousands of miles from the nearest ocean. By the time weather systems reached this far inland, they would have long since dropped all their moisture. This is the simple mechanism that creates such an extreme interior desert. This has a cascade of implications. First, it dramatically limits the size of the habitable land area. Life, which at this point was still fundamentally aquatic, would have been restricted to the coastlines and perhaps a few large river-fed inland seas. The total footprint of the biosphere on the continents would have been tiny. This reinforces the idea that the oceans were the engine of the planet, and the land was a vast, passive, and largely sterile bystander. Second, this geography would have a major impact on global weathering patterns, a key part of the planet's long-term climate thermostat. Chemical weathering, the process that breaks down rocks and consumes atmospheric CO2, is much more efficient in warm, wet conditions. The vast, arid interior of Columbia would have been a zone of extremely slow chemical weathering. This would make the geological part of the planetary thermostat less responsive. The burden of regulating atmospheric CO2 would fall even more heavily on the other main sink, the burial of organic carbon in the oceans. This further strengthens the coupling between the marine biosphere and the global climate. The fate of the planet's temperature was tied even more tightly to the health and productivity of those coastal microbial mats. Third, the configuration of a single supercontinent surrounded by a single superocean would create a very different pattern of ocean circulation. Today's complex network of ocean currents, which efficiently transports heat from the equator to the poles, is a result of the complexer shapes of our modern ocean basins. A single, vast panthalassic ocean would have likely had a simpler, more sluggish circulation pattern. This could have led to more extreme temperature gradients between the tropics and the poles. It also could have exacerbated the chemical stratification of the oceans, making it harder for oxygen from the surface to mix down into the deep, and for nutrients from the deep to well up to the surface. This sluggishness would have further promoted anoxia in the deep ocean and limited the productivity of surface life, reinforcing the stable, low-oxygen state of the world. So, we see that the consequences of having a supercontinent ripple through every part of the Earth system. It changes the climate by creating massive deserts. It alters the carbon cycle by reducing the efficiency of weathering. It reshapes ocean circulation, reinforcing chemical stratification and limiting nutrient supply. All of these effects act in concert to promote the very conditions we've identified as characteristic of the Proterozoic: a small, nutrient-limited biosphere, a low-oxygen atmosphere, and a stable, if somewhat sluggish, planetary state. The geography of the planet was not just a stage for life, it was a primary author of the entire global story. Even the most compelling models must face their strongest criticisms head-on. A scientific theory is only as good as its ability to withstand falsification. So, let's step into the skeptic's corner and outline the most significant challenges to the narrative of a stable, preparatory, boring billion, and consider what evidence could potentially prove this entire framework wrong. The first and most significant criticism comes from the very data that suggests stability. The long, flat line of carbon, isotopes for instance, could be an illusion. Some scientists argue that this signal doesn't reflect a stable global ocean, but rather a change in the way the carbon cycle was recorded in the rocks. For example, if the process of forming carbonate rocks after the sediment was deposited, a process called diagenesis, was widespread and uniform during this period, it could have systematically overwritten the original biological signal, creating an artificial sense of flatness. This is a powerful objection because it questions the reliability of our most important proxy. A potential falsifier for our model would be the discovery of a well-preserved sedimentary sequence from this era that shows large, high-frequency oscillations in carbon isotopes, proving that the system was, in fact, highly dynamic. If we found multiple such locations around the world, the entire stable billion hypothesis would have to be radically re-evaluated. A second major criticism targets the idea of environmental constraint, particularly the role of oxygen. While it's true that large animals need a lot of oxygen, the minimum oxygen requirements for the very first, simplest animals, perhaps tiny, sponge-like creatures, are unknown and possibly quite low. Some recent studies suggest that some modern sponges can survive in extremely low oxygen environments. If this is true, then low oxygen may not have been the hard barrier to the evolution of animal life that we've assumed it to be. The boringness might have been due to some other factor entirely, perhaps a genetic or developmental constraint. The evolutionary machinery to build an animal body plan simply hadn't been invented yet, and the environment was irrelevant. This would be much harder to falsify directly, but one piece of evidence would be a game changer: the discovery of an unambiguous fossil of a simple animal, like a sponge, in rocks from deep within the boring billion, say from 1.5 billion years ago. Such a discovery would instantly prove that animal life could exist in that low-oxygen world, forcing us to rethink the entire timeline of evolution. A third line of attack focuses on nutrient limitation. Our model suggests a nutrient-starved ocean was a key factor in suppressing productivity, but this is inferred indirectly from geochemical proxies. Some critics argue that these proxies can be interpreted in other ways, and that the oceans might not have been as nutrient-poor as we think. They propose that the low productivity was not due to a lack of nutrients, but to the inefficiency of the microbial ecosystems themselves. Perhaps the evolution of grazing, organisms that eat the primary producers, is what's needed to create a more dynamic and efficient food web, And that just hadn't evolved yet. A potential falsifier here would be the discovery of widespread, thick deposits of organic-rich shales from the middle of the Proterozoic. Such rocks would be direct evidence of periods of very high biological productivity, suggesting that nutrients were not, in fact, the primary limiting factor. Finally, we must concede where our model is weakest. The idea of the Proterozoic as a period of cryptic genetic and metabolic innovation is compelling, but it is also the hardest to prove. It's an argument from absence, a way of filling a gap in the fossil record. It is entirely possible that we are inventing a hidden story to explain away a genuine lack of activity. This part of our model is the most speculative and relies heavily on inference from modern genetics, extrapolating backward over 2 billion years. It is a reasonable hypothesis, but we must acknowledge that it has the softest evidentiary foundation. By listing these criticisms and potential falsifiers, we are not weakening our case. We are defining its boundaries. We are saying, this is the model that we believe best fits the available evidence, and here is the kind of evidence that would make us change our minds. This is the hallmark of a healthy scientific process. It keeps the inquiry open and honest, and reminds us that our understanding of this ancient world is, and must always be, a work in progress. Let's take a moment for a meta-method interlude to reflect on the nature of the detective work we are engaged in. Reconstructing a world from 2 billion years ago is not like assembling a puzzle where all the pieces are in the box. It is like trying to understand the blueprint of a cathedral by examining a single, weathered stone from its foundation. The mindset required is one of deep humility, of comfort with ambiguity, and of a constant awareness of the layers of erasure and bias that stand between us and the past. The first layer we must contend with is our own set of priors, the assumptions and mental models we bring to the investigation. As products of the vibrant, high-oxygen, macroscopic world of the Phanerozoic, we have a built-in bias towards seeing complexity, action, and rapid change as interesting and significant. This is why the Proterozoic was so easily labelled boring. Our very definition of an event is skewed. We must constantly challenge this prior, learning to see the profound significance in stability and the deep complexity in a microbial world. The detective must be aware of their own psychological profile, lest they see only the clues they expect to find. The second layer is the nature of the clues themselves. We are hunting for anomalies. In a vast record of apparent stability, a single thin layer of rock with an unusual chemical signature becomes incredibly important. Is this anomaly a local fluke, a meaningless bit of noise? Or is it the first faint signal of a major global change, the one clue that cracks the whole case open? The whiffs of oxygen we discussed earlier are exactly this kind of anomaly. For a long time, they were dismissed as noise. Now, they are seen as potentially crucial evidence for the dynamism hidden within the stable baseline. The detective must have an eye for things that don't fit, and the patience to determine if they are meaningful. The third and most profound layer is the problem of erasure. As we've noted, the geological record is a story of forgetting. Most of the past has been subducted into the mantle, eroded into dust, and cooked beyond recognition. The archives that survive are the lucky few. This means we are working with a profoundly incomplete data set. We cannot assume that the evidence we have is representative of the whole. It's entirely possible that the most important events of the Proterozoic happened in ecosystems or on continents for which no rock record survives. The detective must work with the constant, humbling knowledge that the most crucial clues may be lost forever. This forces us to build models that are not just consistent with the evidence we have, but are also robust enough to accommodate the vastness of what we don't know. This mindset of questioning our priors, focusing on anomalies, and respecting the depth of the erasure is what allows us to move forward. It frees us from the need for absolute certainty and allows us to work in the realm of probabilities and plausible reconstructions. With this renewed awareness of our methodological challenges, let us now reopen the main thread. We have gathered evidence from the scale of a single breath to the scale of the entire planet. We have examined the life, the air, the oceans, the continents, and the very rhythm of the day. We have steel-manned the opposition and considered the ways our model could be wrong. We are now prepared to move toward a synthesis, to begin weaving these threads together into a more holistic and dynamic picture. The task is no longer just to describe the quietness of this ancient world, but to explain its origin, its nature, and its profound consequences. After such a long journey into deep time, across vast, empty continents and into the microscopic world of the cell, it is important to return, once again, to the human scale. To bring the system back to your body, in your room, in this present moment. This is not a retreat from the complexity, but a way of integrating it, of feeling our own place within this immense story. Take another conscious breath. Feel the air enter your lungs. That oxygen you just inhaled was produced by a plant, or perhaps by phytoplankton in the ocean, through the same fundamental process of photosynthesis invented by cyanobacteria billions of years ago. The metabolic machinery in your own cells, the mitochondria that are right now using that oxygen to power your body and your brain, are the direct descendants of the ancient bacteria that form that fateful symbiotic partnership. You are, in a very real sense, a walking, breathing archive of the Proterozoic. The echoes of that ancient world are not just in the rocks beneath your feet. They are written in your own DNA and humming in the engine of your every cell. This realization is not meant to be prescriptive. It does not come with a list of things you should or should not do. It is simply an invitation to a different kind of awareness, an awareness of the deep continuity that connects you to the entire history of life on this planet. Your existence is predicated on a series of evolutionary and geological events that unfolded over an almost unimaginable stretch of time. The long, quiet work of the boring billion, the stabilization of the climate, the patient evolution of the eukaryotic cell, the slow oxygenation of the oceans, was the necessary preamble to your own moment of consciousness. This perspective can subtly shift our sense of agency. We often feel either powerless in the face of vast global systems or burdened by an overwhelming sense of responsibility for them. But seeing ourselves as participants in and products of a 4-billion-year-old system can foster a different feeling, a sense of belonging. You are not separate from this system. You are a temporary but intricate expression of it. The carbon atoms in your body were forged in stars and have cycled through rocks, oceans, atmospheres, and countless other living beings before becoming part of you. You are a momentary eddy in a river of matter and energy that flows through deep time. This embodied understanding changes the nature of the story. It is no longer a detached academic account of a distant past. It becomes a kind of origin story. The narrative of the Proterozoic is the narrative of the construction of the foundational life support systems that you are using right now, in this very breath. It is the story of how the world became a place that could eventually produce a mind capable of wondering about it. So feel the solidity of the ground beneath you, the anchor of gravity holding you in place. Recognize the profound ancientness of the air in your lungs and the metabolic fire in your cells. You are in the loop. You are part of the story. And from this grounded, embodied perspective, we can now turn to one final evidence track before our grand synthesis. Let's introduce one more crucial framework for understanding the planet: the flow of energy. All of the processes we've discussed, from the movement of continents to the metabolism of a single cell, are governed by the laws of thermodynamics. By examining the energy budgets and flows of the Proterozoic Earth, we can understand the fundamental constraints that shaped this world and kept it in its long, stable, low-power state. The ultimate source of energy for the Earth's surface systems is the Sun. As we've noted, the Proterozoic Sun was fainter than it is today. This meant the total amount of incoming solar radiation, the planet's primary energy budget, was smaller. This is a hard, external constraint. The planet had less energy to work with. This simple fact has cascading consequences. It means that to stay warm enough for liquid water, the planet had to be better at trapping the heat it did receive, which points back to the necessity of a stronger greenhouse effect. Now let's look at how that energy was used. A portion of it was captured by the biosphere through photosynthesis. This is the primary energy flow that fuels life. But the efficiency of this energy capture is limited by other factors, namely the availability of nutrients like phosphorus and nitrogen. In a nutrient-limited Proterozoic ocean, the biosphere simply couldn't take full advantage of the available sunlight. Much of that solar energy would have been reflected or radiated back into space without ever entering the biological system. The engine of life was running at a low throttle, not because of a lack of fuel, sunlight, but because of a shortage of essential machine parts, nutrients. This low rate of energy flow through the biosphere had a direct impact on the oxygen cycle. As we've seen, the net production of oxygen is tied to the burial of organic carbon. If the overall rate of photosynthesis, the amount of carbon being fixed in the first place, is low, then the amount of carbon available for burial will also be low. This provides another powerful bottom-up explanation for why oxygen levels remained suppressed. The entire system was energy-starved at its biological base. There simply wasn't enough power flowing through the biosphere to drive a rapid oxygenation of the planet. Let's contrast this with the planet's other great engine, the internal heat engine. This is the energy from the decay of radioactive elements in the Earth's core and mantle. This internal heat is what drives plate tectonics, volcanism, and the slow convection of the mantle. In the Proterozoic, the Earth's interior was hotter than it is today, so this internal engine was running at a higher power. This meant that rates of volcanism were likely higher. Volcanic eruptions release reducing gases, like sulfur dioxide and hydrogen sulfide, which react with and remove oxygen from the atmosphere. Here we have a fascinating asymmetry. The external energy engine, the sun, fueling the biosphere, was running at a lower power than today, while the internal energy engine, geothermal heat, fueling geology, was running at a higher power. This creates a fundamental imbalance. The geological processes that consume oxygen were likely more powerful than the biological processes that produced it. This simple energy budget analysis provides perhaps the most fundamental explanation for the state of the Proterozoic world. The planet was locked in a low oxygen state because the geological oxygen sinks, powered by a strong internal engine, were more than a match for the biological oxygen sources, which were limited by a faint sun and scarce nutrients. This perspective, based on parameters, constraints, and consequences, is powerful because it avoids storytelling and focuses on the underlying physics. The stability of the boring billion was not a mysterious or passive state. It was the inexorable outcome of a planet with a specific energy budget. The system settled into the only state it could, given the amount of energy flowing through its various components. To change the state of the planet, you would need to fundamentally change its energy budget. And that is exactly what eventually happened as the sun brightened, and as biological evolution found new, more efficient ways to capture that solar energy and channel it through the biosphere. The story we've been building from scientific evidence is a modern one, told with the language of isotopes, tectonics, and feedback loops. But the human impulse to understand our world and our origins is not new. For millennia, cultures have created narratives to map the patterns they observe in nature and to explain the creation of the world. It can be a valuable exercise to look at some of these older stories, not as literal truth, but as a different kind of lens, a cultural and metaphorical mapping of similar deep patterns. Many creation myths, from the Babylonian Enuma Elish to the Greek Theogony, begin not with a sudden act of creation out of nothing, but with a pre-existing, undifferentiated, and often chaotic state. There is a primordial soup, a watery abyss, a formless void. In these narratives, the act of creation is one of separation and ordering, the separation of light from dark, of the waters above from the waters below, of the sky from the land. This archetypal pattern of a long, formless state followed by a period of ordering and structure building has an interesting resonance with our geological story. The long, seemingly undifferentiated Proterozoic, a world of microbial mats and stable chemistry, can be seen as a kind of scientific analogue to this primordial state. It was the long, quiet period of before, the necessary ground from which the more structured, differentiated world of the Phanerozoic could eventually emerge. Another common theme in mythology is the idea of a world-shaping battle between opposing forces: order versus chaos, sky gods versus earth monsters. In the Enuma Elish, the god Marduk slays the primordial sea goddess Tiamat and creates the world from her carcass. While our scientific narrative explicitly avoids the language of intention and conflict, we can see a metaphorical parallel in the planet-scale chemical struggle of the Great Oxidation Event. The rise of oxygen-producing cyanobacteria and the subsequent transformation of the planet's chemistry was a kind of revolution, a battle where a new metabolic order, aerobic life, triumphed over the old, anaerobic life. The banded iron formations are the geological scars of this global conflict. This doesn't mean the myths are describing a geological event, of course. It simply means that the pattern of a fundamental, world-altering struggle is a powerful way for humans to make sense of profound transformation. We can also look at narratives that map the relationship between life and the physical. Many indigenous cosmologies do not see a sharp separation between living things and the non-living world of rocks, water, and sky. The entire world is seen as a living, interconnected system where every part has agency and is in relation with every other part. This holistic, systems-based view is, in many ways, more aligned with our modern Earth system science perspective than the mechanistic, reductionist science of previous centuries was. The idea that the biome and the atmosphere are in a constant conversation, that life and the planet are co-evolving, would be perfectly intuitive within many of these cultural frameworks. This cultural lens must be used with care and modesty. We are not claiming that ancient myths contain hidden scientific knowledge. Rather, we are observing that the human mind, across different cultures and eras, may be attuned to certain fundamental patterns in the world, the pattern of a long quiet before a great change, the pattern of transformation through conflict, and the pattern of deep interconnection within a living system. Looking at these stories alongside our scientific model can enrich our understanding, reminding us that the data points of geochemistry are one language for describing the world, but that other languages, rooted in metaphor and narrative, have been trying to tell a similar story of our origins for a very long time. We have now travelled a long way together. We have gathered clues from the colour of the ancient sky, from the rhythm of the tides, from the chemistry of forgotten oceans, and from the very code of life itself. We have built a case for a world that was not boring, but was instead engaged in a billion-year-long project of stabilization and preparation. We have seen how the faint young sun, the closer moon, and the geography of a supercontinent created the physical boundary conditions for this world. We have seen how the planet's systems, both geological and biological, developed powerful negative feedbacks that held it in a state of remarkable equilibrium, and we have seen how, within this stable framework, the slow, cryptic work of eukaryotic evolution was taking place, forging the tools that would one day break that very stability. Now, we are approaching the final turn in our journey. We are about to move from analysis to synthesis, from gathering threads to weaving the tapestry. In the sections to come, we will attempt to integrate all of these evidence tracks into a single, coherent model. We will replace the simple binary opposition of boring versus interesting with a more nuanced continuum of planetary states. We will see the Proterozoic not as a pause, but as a different mode of being, a different way for a planet to be alive. This is the moment where the picture comes into focus. The central intellectual move we need to make now is what I call the turn. It is a deliberate shift in framing, a move away from seeing the world in simple binaries and toward understanding it in terms of continua and spectrums. The question, was the Proterozoic boring or was it interesting, is a false choice. It forces us into an unproductive debate. A more powerful approach is to reframe the question itself. Instead of an either-or, we can propose a range, a continuum of planetary operating modes. Let's imagine a spectrum of planetary states. On one end of the spectrum, you have a dynamic or event-driven mode. This is a world characterized by rapid change, high energy flow, and the regular occurrence of major state shifts. The Phanerozoic eon, with its Cambrian explosion, its multiple mass extinctions, and the rise and fall of dinosaurs and forests, is a classic example of a planet in this dynamic mode. It is a world of high drama and constant innovation at the macroscopic scale. This is the mode we are familiar with and biased toward. On the other end of the spectrum, you have a stable or homeostatic mode. This is a world characterized by low energy flow, powerful negative feedbacks, and long periods of equilibrium. The system is highly resilient to perturbation, and change is slow, incremental, and often cryptic. Our model of the Proterozoic places it firmly on this end of the spectrum. The quietness was the defining feature of this mode. It was a world that had found a deep, stable groove and was powerfully incentivized by its own internal logic to stay there. By replacing the binary with this continuum, we are no longer forced to apply a value judgment. The stable mode is not inherently better or worse than the dynamic mode. It is simply different. It is a different strategy for a planetary system to persist through time. One could even argue that the stable mode is more fundamental. A planet must first learn to be stable before it can afford the high-stakes game of dynamism. The Proterozoic, in this view, was the period when Earth mastered the art of being in the homeostatic mode. It built the resilient, self-regulating systems that would form the permanent foundation for all future, more dynamic states. This turn also helps us translate the abstract model into something closer to lived experience, or even choice. A system's position on this spectrum is not fixed. It is an emergent property of its components, and as we've seen, one of the key components is the biosphere itself. Life can influence the planetary state. The evolution of photosynthesis pushed the planet away from an earlier abiotic equilibrium. The evolution of eukaryotic life and, eventually, animals, with their more energetic metabolisms, provided the push that moved the Earth from the stable mode of the Proterozoic into the dynamic mode of the Phanerozoic. This reframing has profound implications. It suggests that the history of our planet is not a single linear story of progress. It is a story of a system exploring different possible operating modes. It spent its first 3 billion years primarily in a stable, microbial-dominated mode. Then, about 500 million years ago, it crossed a threshold into a new, dynamic, animal-dominated mode. The key insight is that the second mode could not have existed without the first. The long, quiet work of stabilization was the necessary precondition for the subsequent explosion of complexity. The boring billion was the launch pad. This is the turn. It is the move that allows us to hold all the seemingly contradictory evidence in a single coherent framework. The world was stable in its geochemistry, and it was a hotbed of cryptic evolution. It was constrained by its environment, and it was actively creating the conditions for its own future transformation. These are not contradictions. They are the defining features of a planet operating in a homeostatic mode, a mode that we are only just beginning to appreciate in all its quiet, foundational grandeur. With this new framework in place, let's attempt our first pass at a synthesis, integrating the various evidence tracks into a minimal, coherent model of the Proterozoic world 2 billion years ago. We are moving from listing the ingredients to describing the finished dish. Our model begins with the planet's physical and astronomical context. A fainter sun provides less incoming energy, while a hotter interior provides a more vigorous geological engine. A closer moon creates shorter days and larger tides, while also stabilizing the planet's axial tilt and long-term climate. A single supercontinent, Columbia, dominates the geography, creating a vast, arid interior and concentrating the biosphere into its coastal fringes. These are the boundary conditions, the unchangeable rules of the game for this specific moment in Earth's history. Within this context, a planetary system achieves a deep and long-lasting equilibrium. Let's trace the connections. The fainter sun is balanced by a stronger greenhouse effect, keeping the planet temperate. The low oxygen atmosphere, a legacy of the great oxidation event's aftermath, allows for an iron-rich ocean. This ocean acts as a massive chemical buffer, an oxygen sink that readily absorbs the output of the biosphere. The biosphere itself, dominated by microbial mats in the vast, tide-swept coastal zones, is the engine of production. It captures the limited solar energy, but its productivity is capped by the scarce supply of nutrients like phosphorus, which is slowly weathered from the barren supercontinent. Here we see the micro-macro connection in action. The metabolism of a single cyanobacterium in a microbial mat, when multiplied by trillions, produces a small but steady stream of oxygen. This oxygen reacts with iron in the local water column, a process visible at the human scale. This local reaction, integrated over the entire globe and over millions of years, represents a planetary-scale chemical process that regulates the atmosphere and creates the banded iron formations. The entire system is coupled. The rate of tectonics influences the supply of nutrients, which limits the size of the biosphere, which determines the rate of oxygen production, which is then balanced by the geological sinks. This system is locked into a homeostatic state by a series of powerful negative feedback loops. The geological carbon cycle acts as a long-term thermostat. Biologically mediated climate feedbacks like the production of cloud seeding DMS may have provided additional, shorter-term stability. The result is a planet that is incredibly resilient to change. It is a low-power, high-stability system. It is not stuck, it is stable. The quietness is an emergent property of these tightly coupled, well-regulated feedbacks. Into this stable world, a new and revolutionary actor has just been introduced, the eukaryotic cell. This new type of organism, with its compartmentalized structure and its mitochondrial power plants, has far more latent potential than the prokaryotes that built this stable world. But for now, this potential is unrealized. The eukaryotes are living in a world that is not yet optimized for them. Oxygen levels are too low, and the food web is too simple to support the evolution of complex macroscopic forms. So, the Bling Billion is a period of deep tension. On the surface, the planet is in a state of profound equilibrium, humming along in its low-power microbial mode. But, at the microscopic and genetic level, the fuse has been lit. The eukaryotic cell is a ticking time bomb of innovation. For 1 billion years, in the quiet, stable incubators of the Proterozoic oceans, this new biological operating system will be refined, debugged, and prepared. The very stability of the world provides the predictable environment needed for this slow, methodical work. This synthesis avoids triumphalism. It does not present a single, simple cause. Instead, it portrays a complex, interconnected system that has found a temporary but very long-lasting solution to the problem of planetary persistence. It is a model of a world that is simultaneously stable and pregnant with revolutionary potential. The quietness is the sound of a world gathering its strength. A robust synthesis must not only integrate the supporting evidence, but also honestly reconcile the counterpoints and explicitly acknowledge what remains unknown. This second pass at synthesis is about embracing the uncertainty and mapping the frontiers of our knowledge. It is what makes the model a scientific one, rather than just a tidy story. Let's first reconcile the central counterpoint, the stagnation versus stabilization debate. Our synthesis suggests this is a false dichotomy. The system was largely stagnant at the macroscopic and geochemical level, just as the boring billion hypothesis suggests. The evidence for environmental stability is strong. However, our model proposes that this very stasis created the ideal conditions for a different kind of progress, the cryptic, internal evolution of the eukaryotic cell. The planetary scale stability was the crucible in which the genetic and metabolic tools for future macroscopic complexity were forged. So, the model reconciles the two views by proposing that they are describing different levels of the system: stagnation on the outside, innovation on the inside. What about the challenge that oxygen was not the primary limiting factor for the rise of animals? Our model can accommodate this. While we have framed low oxygen as a major constraint, it need not be the only one. The synthesis points to a web of interlocking constraints. Low oxygen, scarce nutrients, and a simple, microbial, only food web. Perhaps the evolution of the first animals required all of these barriers to be removed. It wasn't enough just to have a bit more oxygen. You also needed a more nutrient-rich environment to support a larger biosphere, and you needed the evolution of algae to create a higher quality food source at the base of the food web. The end of the boring billion was likely not caused by a single silver bullet, but by the system crossing multiple interdependent thresholds. Now, let's explicitly name what remains unknown. The single biggest unknown is the detailed history of the eukaryotes during this billion-year period. Our model requires that significant innovation was happening at the genetic level, but the direct evidence for this is sparse. We are inferring this software development phase by looking at the outcome, the Cambrian explosion, and reasoning backward. The next great frontier is to develop new techniques, perhaps molecular paleontology, that analyzes the evolutionary history encoded in the genomes of modern organisms, to try and put a timeline on these ancient genetic innovations. Another major area of uncertainty is the precise tuning of the planetary thermostat. We have sketched out a model with multiple feedback loops, but the relative importance of each one is still hotly debated. Was the climate primarily stabilized by the geological carbonate-silicate cycle, or did biological feedbacks like DMS production play a more significant role than we currently assume? Answering this requires more sophisticated climate models of the deep past, constrained by more precise geochemical data from the rock record. Finally, we must acknowledge the role of sheer contingency. Our model describes a deterministic-looking system of feedbacks and constraints, but history is also shaped by chance. The evolution of a key innovation, like endosymbiosis, might have been an incredibly rare chance event. If that event had never happened, would Earth still be in a microbial-dominated state? We don't know. How much of our planet's story is the inevitable result of planetary physics and chemistry, and how much is the result of frozen accidents, the unpredictable twists and turns of evolutionary history? This is perhaps the deepest and most difficult question of all, and it marks a clear boundary of our knowledge. By mapping these uncertainties, our synthesis becomes more honest and more useful. It is not a final answer. It is a working model, a platform for asking better questions. It tells us where to look next, for the hidden history in the genome, for the subtle signals of climate, feedbacks in the rock record, and for a deeper understanding of the interplay between necessity and chance in the evolution of a habitable planet. To make this grand synthesis feel tangible, let's walk through it one last time, using a vivid, step-by-step causal chain. We will place you, the observer, inside the system, watching it operate as a single, integrated whole. You are witnessing the Earth system 2 billion years ago. The story begins with energy. The sun, your planet's ultimate power source, is faint. This is the first constraint. To avoid freezing, your world must hold onto its heat, which it does through a thick blanket of greenhouse gases. Simultaneously, the planet's core is hot, driving a vigorous tectonic engine that builds continents and fuels volcanoes. This is the second constraint. Now, watch how life responds in the shallow, sunlit coastal waters of a vast supercontinent. Microbial communities capture the faint sunlight. This is photosynthesis. But their growth is limited. The barren continent weathers slowly, providing only a trickle of essential nutrients like phosphorus. The biosphere is, therefore, small and nutrient-starved. This is a crucial link in the chain. Because productivity is low, the amount of organic carbon that gets buried in the seafloor is also low. Follow the consequences of this low-carbon burial. First, it means that the biological pump drawing down CO2 from the atmosphere is weak. This helps the planet stay warm, counteracting the faint sun. Second, and critically, it means that the net production of oxygen, the waste product of photosynthesis that is left behind when carbon is buried, is also very low. You have a small, steady trickle of oxygen being added to the system. Now, look at the other side of the ledger. The oxygen sinks. The hot, active geology of your planet is constantly pumping, reducing volcanic gases into the atmosphere, which instantly consume oxygen. The rivers washing off the continent are pouring dissolved iron into the oceans. This iron-rich seawater is a vast chemical sponge, soaking up any free oxygen it encounters. The sinks are enormous, and they are more than a match for the small biological source. This is the heart of the system. A faint sun and scarce nutrients lead to low biological productivity. Low productivity leads to low oxygen production. This small oxygen source is overwhelmed by the vast geological oxygen sinks. The result, the inevitable outcome of this chain of causality, is a planet with a stable, temperate climate and a low oxygen atmosphere. You are not witnessing a system that is broken or paused. You are witnessing a system in perfect, logical, long-term equilibrium. Now, zoom into a single drop of seawater. Here, you see the seeds of the future. Among the simple bacterial cells, you see a new kind of entity, a larger, more complex eukaryotic cell. It is struggling. In this low-energy, low-oxygen world, its sophisticated machinery provides little advantage. It is a high-performance engine forced to run on low-grade fuel. But it is surviving, and as it survives, it is slowly, randomly, through mutation and selection, refining its internal systems. It is developing new ways to regulate its genes, new proteins for new functions, new methods for communicating with its neighbors. This is the hidden dynamic. On the planetary scale, you see a system locked in a stable state, but at the cellular scale, you see a system of immense latent potential, slowly gathering its strength, waiting for the global conditions to change. You understand now that the stability of the whole is the very thing that allows for the slow, protected innovation in the part. The quietness of the planet is the incubator for the revolution to come. The entire story is right there, in the contrast between the stable chemistry of the ocean and the roiling, nascent complexity within a single cell. This deep-time perspective, this understanding of the Earth as a slow-moving, interconnected system, is not just an intellectual exercise. It can be translated into a set of small, testable practices for how we pay attention to the world and how we understand our own agency within it. These are not moral prescriptions, but rather invitations to a different kind of perception, framed from a local first perspective. The first practice is to cultivate systems sight. The next time you experience a piece of weather, a rainstorm, a heatwave, a windy day, try to consciously trace its connections. This rain is not just water falling from the sky. It is part of the global water cycle, a system that has been operating for billions of years. The water in that raindrop may have once been in a Proterozoic ocean. The energy driving the storm comes from the sun, and its path is shaped by the rotation of the Earth. This practice is about looking at any single event and asking, what larger system is this a part of? What are the flows of energy and matter that are making this happen? It shifts your focus from the isolated object to the web of relationships that surrounds it. A second practice is to notice the slow variables. Our attention is naturally drawn to fast-moving events, the daily news, the changing seasons. But the most powerful forces shaping our world are often the slow-moving ones that operate on timescales of decades, centuries, or millennia. Things like soil formation, the movement of tectonic plates, or the gradual change in atmospheric composition. You can practice this locally. Look at an old tree and consider the decades it has been interacting with the local soil and climate. Look at a river valley and imagine the thousands of years of erosion that carved it. This practice is an exercise in recalibrating your sense of time, of learning to see the profound power of slow, incremental change. A third practice involves recognizing your own metabolism as an ecological act. Every meal you eat and every breath you take is a transaction with the planetary system. The food you eat connects you to the soil, the water cycle, and the nitrogen cycle. The oxygen you breathe connects you to the global community of photosynthetic organisms. This is not about feeling guilty or anxious. It is about fostering a simple, non-judgmental awareness of your own embeddedness. You are not just living on the Earth, you are a manifestation of the Earth. This practice grounds the vast, abstract story of biogeochemical cycles in the most intimate reality of your own body. These practices, cultivating systems sight, noticing slow variables and recognizing your metabolic embeddedness, are small ways to bring the wisdom of the deep past into the present moment. They don't require you to solve the world's problems. They simply ask you to see the world and your place in it a little more clearly. They shift the frame from a world of separate, competing objects to a world of interconnected, co-evolving systems. It is a way of experiencing the quiet, foundational logic of the Proterozoic in the fabric of your daily life. What does the future hold for a planet like Earth? Our journey into the deep past provides a powerful context for thinking about the future, not by offering specific predictions, but by revealing the fundamental principles that govern planetary change over long timescales. This is bounded speculation, an attempt to map out plausible scenarios and open questions with our confidence levels clearly labelled. In the near term, on the scale of centuries to millennia, the open questions revolve around the stability of our current planetary state. We are living in the Phanerozoic, the dynamic mode, but we are also conducting an unprecedented experiment by rapidly altering the composition of the atmosphere. The key question, informed by our Proterozoic model, is this: how resilient are the Earth's current stabilizing feedbacks? Are we approaching a tipping point that could shift the planet into a new and potentially much less hospitable, stable state? The deep past teaches us that such state shifts are a normal part of Earth's history. The planet has been a hothouse world with no ice caps before, and it has been a snowball world covered in ice. The system is capable of finding new equilibria. The urgent question for us is where the thresholds lie. Our confidence here is low for specifics, but high for the general principle. Complex systems can and do undergo rapid, non-linear state changes when pushed past a certain point. In the longer term, on the scale of millions to hundreds of millions of years, the future will be shaped by the slow, powerful forces of geology and astronomy. Plate tectonics will continue its relentless march. The continents will drift, oceans will open and close, and in roughly 250 million years, they will likely assemble into the next supercontinent. The consequences of this will be profound, echoing the world of Columbia. A new supercontinent would create vast interior deserts, alter ocean circulation, and fundamentally reshape the global climate. We can be highly confident this will happen. The details of the geography are what remain speculative. Simultaneously, the sun will continue to brighten, a steady, inexorable process. In about 500 million to a billion years, this increase in solar radiation will begin to overwhelm the planet's geological thermostat. The carbonate-silicate weathering cycle will no longer be able to cool the planet sufficiently. Temperatures will rise, and the oceans will begin to evaporate at a much higher rate. This will trigger a runaway greenhouse effect, eventually boiling the oceans away and rendering the planet's surface sterile. This is not a speculative risk. It is a straightforward astrophysical prediction. Earth's time as a habitable planet for complex life is finite. Our confidence in this long-term outcome is very high. This long view raises a profound open question. Is the transition from a microbial world to a world of complex intelligent life a common occurrence on planets, or is it an exceedingly rare fluke? The boring billion suggests that the window for complex life might be narrow. A planet might spend most of its habitable lifetime in a stable microbial state. Perhaps the transition to a dynamic, macroscopic world only happens late in a planet's life, just a few 100 million years before the brightening sun makes such life impossible. This is the Gaian bottleneck hypothesis. If true, it would suggest that the universe might be teeming with microbial life, but that planets with animals and intelligence are exceptionally rare. This is one of the biggest open questions in science, and our own planet's history is our only data point. By looking at these future directions, we see our present moment nested between two immense quiet periods. Behind us lies the long, stable quiet of the Proterozoic. Far ahead of us lies the final, sterile quiet of a post-habitable Earth. Our dynamic, noisy, complex era is a temporary phase, a brief, exuberant flowering in the vast silence of cosmic time. How does this intellectual journey translate into felt meaning? We have built a complex, multi-layered model of an ancient world. We have talked about feedback loops, isotopes, and tectonics. But what does it all feel like? What is the emotional resonance of this deep time story? The goal here is not to find a simple moral, but to explore the emotional reframing that this perspective can offer, using the same calm, low-heat cadence that has guided our entire exploration. The first feeling that often arises is one of profound humility. To see our entire species, our entire history, as a momentary flicker in the last few seconds of the planetary year is to be put in our place. Our dramas, our triumphs, our anxieties, which feel so all-encompassing, are cast in a new light. They are not rendered meaningless, but they are contextualized within a much larger and older story. This is not a diminishing humility, but an expansive one. It connects us to something vast and enduring. It is the feeling of standing on a mountaintop and seeing the world stretch out below, a feeling of being both very small and part of something magnificent. A second feeling is a sense of deep time as a source of solace. The world we have explored tonight was stable, resilient, and self-regulating. It survived and persisted for 1 billion years. Life on this planet has weathered crises far greater than any we are currently facing, from planetary collisions to global oxygen poisoning to asteroid impacts. The system is tough. The threads of life are ancient and deeply woven into the fabric of the planet itself. This does not absolve us of our responsibilities in the present, but it can be a source of a quiet, non-anxious hope. It reminds us that our story is part of a much longer story of planetary resilience. There is a deep, slow, quiet strength in the Earth system, a strength that operates on timescales far beyond our own. Finally, this journey can cultivate a feeling of profound belonging. We have seen how our own bodies are archives of this deep history, how our metabolism is a legacy of ancient microbial innovations. We are not aliens who arrived on this planet. We are the planet itself, evolved to a state of self-awareness. Every element in our bodies was forged in the crucible of geology and biology. This perspective dissolves the imaginary boundary between us and nature. You are not a visitor in this world. You are a participant. You are a temporary pattern, a brief flowering of the same ancient matter and energy that built the stromatolites and tinted the Proterozoic seas. This is a quiet, powerful form of homecoming. These feelings, humility, solace, and belonging, are not loud or dramatic. They are the emotional equivalent of the Proterozoic world itself. Quiet, stable, and foundational. They are the emotional reframe that emerges when we allow the intellectual model to sink in, to move from the head to the heart. It is the felt sense of our own place in the long, slow, and deeply meaningful story of this living planet. We have reached the edge of our map. We have followed the trails of evidence as far as they can take us, building a model of a world that is both scientifically plausible and imaginatively resonant. But here, at this boundary, we must acknowledge that data can only take us so far. The scientific method is a powerful tool for understanding how the world works. It is not designed to answer the question of why. This is the philosophical boundary, the place where data stops and the search for meaning begins. Our scientific narrative has described the emergence of life and the co-evolution of the planet as a series of contingent events governed by the laws of physics and chemistry. It is a story of process, not purpose. From this perspective, the boring billion was not for anything. It did not happen in order to create the conditions for humanity. It was simply a stable state that the Earth system settled into, and the evolution of the eukaryotic cell within that state was a happy accident, a fortunate turn of events that eventually led to us. The universe, in this view, is indifferent. Meaning is not something we discover in the data. It is something we, as conscious beings, create and assign to the world. But this is not the only way to interpret the story. One could look at the same set of facts, the incredible fine-tuning of the physical constants that allow for a stable universe, the remarkable resilience of life, the seemingly directional trend toward increasing complexity over billions of years, and see the signature of something more. One could perceive a purpose, a direction, a telos, in the unfolding of cosmic and biological history. In this view, the long, quiet preparation of the Proterozoic was not an accident, but a necessary and meaningful chapter in a grander narrative, a story that was, in some sense, always headed toward the emergence of complexity and consciousness. The critical point is that the scientific evidence itself cannot distinguish between these two interpretations. A person of faith and a person of no faith can look at the very same banded iron formation and agree completely on the geochemical processes that formed it. They can agree on the low oxygen state of the ocean, the role of cyanobacteria, and the age of the rock. The data is the same for both. The divergence happens at the level of interpretation, at the level of meaning. Does this intricate, self-regulating, 4-billion-year-old system point to something beyond itself? Or is its intricate, self-regulating nature simply a fascinating and beautiful emergent property of matter and energy? Our project tonight has been to stay on the data side of this boundary. We have tried to build a model that is as free as possible from teleological language and assumptions of purpose. But it is important and intellectually honest to acknowledge that this boundary exists, to hold the question of ultimate meaning open without rushing to a verdict. Science can provide us with a powerful and awe-inspiring creation story, a narrative of our origins that is grounded in evidence and reason. But it cannot, and does not, claim to have the final word on what it all means. That is a question that each of us must continue to ask for ourselves, a quiet inquiry that sits at the very heart of the human experience. As we approach the end of our journey, let's consider two final, overarching frames for making sense of the intricate, life-sustaining world we have been exploring. One is the frame of emergence, and the other is the frame of anthropic selection, or, for some, design. These are not necessarily competing explanations to be fought over. They can be seen as two different languages for expressing a shared sense of wonder and humility in the face of a system that is far more complex than we can fully comprehend. The first frame, emergence, is the native language of complexity science. From this perspective, the remarkable properties of our planet, its long-term stability, its self-regulating climate, the intricate dance of its biogeochemical cycles, are not imposed from the top down. They are emergent properties that arise from the bottom up, from the simple interactions of countless individual components. The planet is not managed by a central controller. Homeostasis is not a goal the system is trying to achieve. It is a pattern that naturally emerges when you have a vast network of interacting parts with feedback loops. In this view, the wisdom of the system is not located in any single part, but is distributed throughout the entire network. Life doesn't just adapt to a passive planet. Life and the planet adapt to each other, co-creating the world in a continuous, unscripted dance. The story is one of spontaneous self-organization. The second frame approaches the question from the opposite direction. It starts with the observation that we are here, as conscious observers, asking these questions. This is the anthropic principle. The fact of our existence acts as a powerful selection filter on the kind of universe we must inhabit. For us to be here, the universe must have had the right physical laws. The planet must have been in the right location, had the right ingredients, and remained habitable for billions of years. From this perspective, it is not surprising that we find ourselves on a planet that looks perfectly suited for us. We could not have evolved anywhere else. This doesn't explain how the system came to be this way, but it explains why we observe it to be so. For some, this line of reasoning points toward the idea of a designer, a creator who set up the initial conditions with the intention of producing life. For others, it might suggest we are living in a multiverse, and we naturally find ourselves in one of the rare universes where the conditions are just right. What is remarkable is that both of these frames, whether you prefer the language of emergence or the language of anthropic selection, lead to the same place, a profound sense of humility and awe. The person who sees the Earth as a self-organizing system is awed by the power of simple rules to generate seemingly miraculous complexity. The person who sees the Earth through an anthropic lens is awed by the sheer improbability and good fortune of our existence. Both are humbled by the intricate, life-sustaining elegance of the world. We do not have to choose between them. We can hold them as parallel, non-combative ways of framing the same deep mystery. They are different windows looking out onto the same landscape. Whether you see the stability of the Proterozoic as the result of a blind, emergent process, or as a necessary step in a purposeful cosmic story, the result is the same. A billion years of quiet, foundational work that made our own noisy, conscious moment possible. The two frames share the same conclusion. We are part of something very old, very complex, and very precious. And so, we arrive at the final turn, the one that brings the entire journey home to you. We have travelled across 2 billion years of time, from the vastness of a supercontinent to the inner world of a single cell. We have seen the Earth as a complex, interconnected system. The final step is to locate yourself, personally, inside that system. This is the move from intellectual understanding to a feeling of personal belonging. You are not merely an observer of this system. You are an active, breathing, metabolic component of it. The boundary between your body and the world is a permeable membrane, not a solid wall. With every breath you exchange gases with the atmosphere, participating in a cycle that has been turning since the first cyanobacteria. With every drink of water, you are borrowing from the same planetary reservoir that has filled the oceans for eons. The minerals in your bones and the iron in your blood are drawn from the Earth's crust, the same geological reservoir that shaped the chemistry of the Proterozoic world. This is not a metaphor. It is a literal, physical truth. You are in the loop. The feedback systems we have been discussing are not abstract concepts happening out there. They are happening through you right now. Your body's own homeostatic systems, the regulation of your temperature, your blood sugar, your pH, are a small fractal echo of the planetary scale homeostasis that governed the Proterozoic. You are a microcosm of the macrocosm. This realization brings with it a quiet form of agency. It is not the heroic agency of saving the planet, which can feel overwhelming and abstract. It is the intimate, embodied agency of being a conscious participant in the system. The way you choose to live, the things you pay attention to, the way you interact with your local environment, these are all ways of tuning your own small part of the larger network. This perspective doesn't demand that you become an expert on climate science or geology. It simply invites you to be more present to your own life as an ecological and planetary process. See your consciousness not as something separate from the world, but as a property that the system itself has evolved. The Earth, after 4 billion years of slow, methodical evolution, has produced a part of itself that is capable of reflecting on the whole. You are the planet's way of knowing itself. The curiosity that has guided our journey tonight is not just your curiosity. It is an expression of the universe's own inherent tendency to become aware of itself. This is the ultimate sense of belonging. You are not a stranger here. You are made of the stuff of this place, the stardust, the rock, the water, and the ancient breath of microbes. You are a descendant of the survivors of every crisis, a beneficiary of the long, quiet work of stabilization. You belong to this story, and the story belongs to you. And so, we have come full circle. We began with a simple question, born of a quiet moment of curiosity. What was Earth really like 2 billion years ago? We embarked on a journey, not to find a single definitive answer, but to build a plausible and resonant model of that lost world. We travelled back in time, stripping away the familiar features of our modern Earth to reveal a stranger, more elemental planet. We stood under a pale orange sky and looked out at a pale green ocean. We felt the pull of a closer moon and the rhythm of a shorter day. We journeyed into the vast, sterile heart of a supercontinent and marvelled at the thin, vibrant fringe of microbial life that clung to its coasts. We explored the planet as a system, learning to see the intricate web of feedback loops that held it in a state of profound stability for 1 billion years. We saw this quietness not as a sign of stagnation, but as the signature of a mature, self-regulating world engaged in the slow, foundational work of building a resilient biosphere. We saw, in the cryptic evolution of the first complex cells, the seeds of a future evolution being quietly sown within that stable incubator. We grappled with the limits of our own knowledge, acknowledging the fragmentary nature of the deep time archive and the biases inherent in our own perspective. We held competing interpretations in parallel and sought a synthesis that could honour the complexity and the uncertainty of the story. And now, at the end of this long exploration, we can re-ask our core question, but with a new depth of understanding. What does it mean for a world to be quiet, and what kind of power is held in that quietness? Perhaps the power held in that quietness is the power of persistence, the power of patient incremental work, the power of building a foundation so strong and so deep that it can support the explosive, unpredictable and beautiful dynamism of all the ages to come, including our own. As our time together comes to a close, I want to extend a simple and heartfelt thank you. Thank you for your attention. Thank you for your curiosity. In a world that so often demands speed and certainty, it is a rare and valuable thing to be able to spend time together in a space of slowness, of questioning, and of shared wonder. This journey we've taken is not a passive one. It requires a certain kind of focus, a willingness to hold complex ideas, and to travel in your imagination to places that are abstract and unfamiliar. Your presence here, your engagement with this story, is what gives it life. These are not just words being spoken into a void, they are ideas being shared in a community, however scattered and asynchronous that community may be. If you have found this exploration meaningful, I hope you will carry its echoes with you. There is nothing more to do, there is no call to action, other than perhaps to continue to nurture your own sense of curiosity about the world and your place within it. The greatest gift of these deep time stories is the perspective they offer, a quiet recentering that can follow us back into the noise and bustle of our daily lives. Thank you for being here, thank you for listening, and so we let the tension release, we let the story settle. The journey into the deep past is over, but the sense of wonder it instills can remain. The goal was never to arrive at a final closed answer, but to open up a space for a deeper and more intimate relationship with the planetary story we are all a part of. We end not with a conclusion, but with a quiet landing, a return to the present moment, enriched by the echoes of an ancient world. The questions remain, and that is as it should be. The mystery of our origin, of how this particular configuration of matter and energy on a small rocky planet could lead to consciousness and curiosity, is not a problem to be solved. It is a wonder to be lived in. The quietness of the Proterozoic was a quietness of preparation. Perhaps our own moments of quiet, of stillness, of non-doing are also a form of preparation, a way of allowing for the slow, foundational work of understanding to take root. Let the details of the science fade, if they will. Let the specific names and numbers recede. What is meant to remain is a feeling of immense timescale, of intricate connection, and of your own profound physical belonging to this long and unfinished story. The answers are provisional, but the awe is durable. Hold on to the awe. Let it be the quiet hum beneath the surface of your days. There is no need to grasp for a final meaning. The meaning is in the inquiry itself, in the shared act of looking back and wondering. Now come back one last time to the room where you are. Notice again the air, that mixture of gases that sustains you. Think of its long journey from the anoxic beginnings, through the great oxygenation, through the long, stable quiet of the Proterozoic, to this very moment, entering your lungs. It is an ancient atmosphere, constantly recycled, a shared commons that connects you to every living thing on the planet, past and present. Consider the materials around you, the metal and silicon in the device you are listening on, the minerals in the concrete of the building, the wood in the floor. Every solid object is a piece of the Earth's crust, a product of geological processes that have been unfolding for billions of years. The stuff of the planet is not just out there, it is here, in your hands, supporting your body, forming the very architecture of your world. This is the final echo. The story of the macrocosm, the story of the planet's becoming, is mirrored in the microcosm of your immediate sensory reality. The deep past is not truly past. It is latent in the present, in the air, in the materials in your own body. The quiet, foundational world of 2 billion years ago is still here, humming quietly beneath the surface of everything. You are breathing its legacy. You are living within its architecture. And for a moment, you have been able to hear its story,